Okay. Yes. All right. So very good evening all. Now let us discuss some numericals related to the voltage commutated chopper and current commutated chopper. We have already discussed these commutation circuitries during the discussion of the chapter number 1, right? So let us discuss this numerical. In the following circuit, the inductance carries a initial current of 200 ampere and initial voltage across the capacitor is equal to the source voltage. Okay, so here important thing is it is given that the initial current flowing through the inductor is a non-zero. Initial voltage across the capacitor is also non-zero, and capacitor voltage is same as that of the supply voltage, that is equal to 100 volt. Okay, determine the conduction time of SCR and the capacitor voltage at turn off. Okay, our task is to find the conduction time of this SCR and the capacitor voltage at the instant of turning off, right? So now let us first understand this circuit. In this circuit, if you check, before this we have already analyzed this type of circuit. This is like your load commutation circuit na, right? Very first commutation circuit we discussed, that is the load commutation circuit. Okay, so in that case actually the thing was inductor initial current and capacitor initial voltage was 0. Okay, and from that we got the expression of the current I is equal to, it is like Vs into under root C by L into sine of omega 0 t. Yes or no? Right? Now the same expression will hold here. The only thing is we need to add the initial conditions also, right? We need to add the initial conditions also, right? So now here, yes, suppose if we apply the KVL to this loop first, if we apply the KVL to the loop, okay, so suppose for t greater than 0, it is like a thyristor is turned on and I am applying the KVL. So let me write for t greater than 0, if we apply the, if we draw the circuit, it will be like this. Thyristor is acting as a short circuit. Here it is a capacitor and here it is a source, right? This voltage is equal to 100 volt, or you can write it as a VDC also, doesn't matter. This is a 10 microhenry. This current is I0 they have given, that is the initial current. Thyristor T, capacitor C, capacitor value is 50 microfarad, and capacitor is having an initial voltage which is equal to same as that of the supply voltage, right? So as soon as thyristor turns on, definitely the current will flow into the circuit, right? So when the current flows through the circuit, right, when the current flows through the circuit, okay, we can apply the KVL to loop. So this can be written as plus 100, or you can write plus VDC. In general, the expression we will write VDC minus L into di by dt. So it is a L into di by dt minus 1 by C integration of I into dt is equal to 0, right? So further I can write it as VDC is equal to L into di by dt plus 1 by C integration of I into dt. Now if we simplify it with the help of Laplace transform, yes, so yes, taking Laplace transform on both the sides, so it will be like, be careful, VDC is a constant, so Laplace will be VDC by S, which is equal to, here we are having the L into di by dt, definitely its Laplace will be L into S I of S, but here be careful, the initial current flowing through the inductor is a non-zero, yes or no? So we need to consider that initial current also. Okay, so here if we take the initial current flowing through the inductor, then it will be like L into, as it is, this is a S into I of S minus, we need to consider the initial current, that is a I0, plus the capacitor, so it is a 1 by CS, right, 1 by C into bracket, it is like a S into I of S, S into I of S plus the initial voltage across the capacitor that we need to consider. Okay, so generally it is represented with C into VDC, okay, divided by the thing is, it is a S. Okay, This is by using the initial condition. And after this, if we simplify it, we'll be getting the expression for the current I. Okay, so it will be like I is equal to the expression, if you recall, whatever we already derived in the previous case, that is without capacitor initial voltage and without capacitor inductor initial current. It was like Vs into under root C by L. Na? So here it is like a Vs, but only thing is here the initial capacitor voltage will be getting added here. Why? Because capacitor is charged like this, plus here minus here. So capacitor voltage and here supply voltage will be opposite to each other actually. Okay, so it is like a Vs minus Vdc into under root C by L into sine of omega 0 into t plus the initial current, that is a I0 into cos of omega 0 t, right? So this is the expression of current in the circuit, So always keep it in mind. If initial capacitor voltage is 0, inductor current is 0, if initial I am saying, then the expression is like I is equal to Vs under root C by L sine of omega 0 t, that's it. But if initially the inductor is carrying some current and capacitor is also charged, then the thing is here we need to check the polarity of the voltage across capacitor. Accordingly, we need to change here into under root C by L sine of omega 0 t as it is, plus I0 into cos of omega 0 t, right? So now here you can check in our case, here capacitor voltage is same as that of the supply voltage. Now they have given the capacitor has charged, initial voltage across the capacitor is equal to the source voltage. Okay, so initially capacitor is charged to the voltage of same as that of the source voltage. So in reality this will become 0. So can I write it as I is equal to, it is like a Vs minus Vs or Vdc minus let me write it as 100 minus 100. That will be good. Into under root C by L. C value is 50 micro divided by L value is 10 micro, right? Into sine of omega 0 t plus initial current flowing through the inductor. It is 100. Okay, sorry, 200 into cos of omega 0 t. So if you check, this term will become 0, right? Because it is 100 minus 100. So only thing is I is equal to, therefore I is equal to, will be getting it as a 200 into cos of omega 0 into t, right? This is the current in the circuit. Now if you check in the question, determine the conduction time of the SCR. So if this is the current in the circuit, 200 into cos of omega 0 t, right? So from this, can we say that, yes, from this, can we say that the nature of the current in the circuit is like this? This is like omega t 0, or let me write it as a t only. So current in the circuit will be like this. It is a co-sinusoidal waveform. Okay. Yes. Co-sinusoidal waveform. So here it is a peak value, that is a 200. Here it is a 0 now. So now you can check what is the time corresponding to this instant. Time corresponding to this instant is t is equal to cos of pi by 2 is 0 now. So can I say that t is equal to pi by 2 by omega 0, that is pi by 2 omega 0, right? So this is like pi upon 2 omega 0. Are you getting the point? Okay. So at t is equal to pi by 2 omega 0, it is like current in the circuit will become 0. If the current in the circuit will reach the 0 value, the meaning is the first condition for the commutation as thyristor is reached. Na? So that's why our thyristor will turn off. So the thing is, our thyristor will be in a conduction mode only till which instant? 0 to pi by 2 omega 0. So what is the conduction time of thyristor? Conduction time of thyristor is only pi by 2 omega 0. Are you getting the point, right? So as at t is equal to pi by 2 omega 0, current flowing through circuit I reaches 0 value. I reaches 0 value. That is current through thyristor. Current through thyristor T becomes 0. Current through thyristor T becomes 0. Okay. So therefore, thyristor T turns off. Thyristor T turns off, right? So thyristor T turns off. So therefore, Shravan Kumar, do you want to say something? So here, therefore, yes, conduction time of thyristor. Thyristor is equal to pi upon 2 omega 0, right? So pi by 2 omega 0. So here you can check pi by 2 omega 0. Omega 0 is 1 by root LC. So can I write it as, which is equal to pi by 2 upon 1 by root LC. Okay, 2 into 1 by root LC. So it is like pi root LC divided by 2 now. Pi root LC divided by 2, right? So you can check it is pi into under root L and C. L value is we are having 10 micro and C is 50 micro. So 10 into 10 to the power minus 6 into 50 into 10 to the power minus 6 divided by 2, right? So please check how much. Please check once. I will join you shortly. Okay, within a short time I will join. Yeah, please check the answer. Yes, it is 34.124. Okay, 35.124, right? 35.124 microsecond. 35.124 microsecond, right? So this is the first thing. Naveen, please check once. You are saying 0.11. Some students are saying don't understand the Laplace. Okay. Yes. Yes. Yes, we need to take the Laplace of this thing. Laplace of this term. VDC is constant, so Laplace of VDC is VDC by S. Okay, VDC by S. Okay, plus is equal to what? We are having the L as it is, Laplace of differentiation. But here we need to understand, we need to use the property of the Laplace that is with the non-zero initial condition. What is the Laplace of di by dt? It is a S into I of S. Okay, and again I need to consider that initial condition as well. Okay, so that's why here I have taken it as a S I of S minus I0 plus 1 by C as it is, Laplace of integration. It is a 1 by S, na? Right? So it is 1 by S into I of S. Yes, here it should be, correct. It is a 1 by C into I of S divided by S. Okay. Plus, we need to check the initial voltage across the capacitor also we need to consider. It is C into VDC by S. Are you getting the point? Right? Yeah. Because this CC will get cancelled out, then you will be getting this initial voltage, that is a VDC like thing. Okay, so next, so 35.124. Second bit they asked the capacitor voltage at a turn off. Capacitor voltage at the instant of turning off. Okay, now the thing is, once this thyristor turns on, here we are having an inductor. This inductor allows the change in a current. So initially inductor current is a 200 ampere. So that's why what will happen, even though the capacitor is charged to the voltage of 100 volt, due to this inductor, our capacitor will be getting yes, charged to the more voltage, charged to the more voltage. To which voltage the capacitor will be getting charged, that we need to find. Okay, that we need to find. Okay, so how to find the voltage across capacitor for t greater than 0? Yes, let me use voltage across capacitor for t greater than 0. So again, for t greater than 0, voltage across capacitor, voltage across capacitor, that is Vc. Yes, we know Vc is equal to 1 by c integration of I into dt. 1 by c integration of I into dt. Now the thing is, you can check this circuit. Capacitor inductor current is in the direction from left to right. Okay, capacitor charge to the voltage, it is plus here minus here to the 100 volt. This inductor will, this due to this, as this inductor will go on releasing the energy now, so due to that again our capacitor will be getting charged. Okay, and to how much voltage it will be charged, it depends on, yes, your current, this current in the circuit, and at the same time the instant till which this switch will be in a conduction mode. We already yes, identified the instant at which till which the switch is in a on state. That instant is your 35.124 microsecond. Okay, now in this case it is 1 by c integration of I into dt plus the initial voltage across capacitor. It is a VDC now, it is 100 volt they have given. Okay, so if you check, it is 1 by c. Now what is the current in the circuit? You can check, we have written here current in the circuit. Yes, it is a 200 into cos of omega 0 t, right? 200 into cos of omega 0 t. So let me write here 200 into cos of omega 0 into t into dt plus VDC. So which is equal to, let me put C also here, 1 by C is equal to 50 microfarad. 50 into 10 to the power minus 6 into, let me take 200 outside. So it is 200 upon 50 into 10 to the power minus 6 into integration of cos is sine of omega 0 t divided by omega 0 plus VDC, right? Plus VDC. So here you can check, it is like a 200 divided by 50 into 10 to the power minus 6. Omega 0 is 1 by root LC. So here it will be like into root LC will be getting added. Okay, into sine of omega 0 into t plus VDC. This is a VC. Now further we can write this term VC. So therefore VC is equal to, yes, 200 divided by 50 means it is a 4 into 10 to the power plus 6 into root LC na. So under root L into C. So you can check L value are having 10 micro, C is a 50 micro. So it is a 10 micro into 50 micro. Into, it is a sine of omega 0 t plus VDC is 100 na, so plus 100. So if you check, this term is under root 500 into 10 to the power minus 12 into 4 into 10 to the power 6. So it is equal to 89.44 into sine of omega 0 t plus 100. This is the expression for VC. But you can check, the thyristor is in a conduction mode only till t is equal to pi by 2 omega 0 na, right? So our task is to find the voltage across the capacitor at the instant of, yes, turning off of a thyristor. Okay, so therefore voltage across capacitor, therefore VC at t is equal to pi by 2 omega 0. Simply I need to replace this t with pi by 2 omega 0. So therefore I can write VC is equal to 89.44 into sine of omega 0 into pi by 2 omega 0 plus 100. Okay, so it is like omega 0 cancel out. So it is sine of pi by 2. Sine pi by 2 is 1. Okay, so it is equal to 100 plus this term. So it is a 189.44 volt. This is the voltage across capacitor at the instant of commutation of your thyristor. At the instant of commutation of the thyristor. Is this clear? Right? Okay. So please try to understand here. The thing is, initial voltage across the capacitor and current flowing through the inductor is non-zero, they have given. Okay, so that's why we need to simplify this circuit by using the non-zero initial condition of the Laplace transform, right? Okay, next, yeah, let us discuss this example. A voltage commutated chopper has the following parameters. Voltage commutated chopper means your voltage commutation circuit. Okay, that we already discussed. Vs is 220 volt. Load circuit parameters 0.5 ohm, 2 millihenry, and 40 volt. That is a RLE load is there. Commutation circuit parameters: inductor is 20 microhenry, capacitor is 50 microfarad. T on is 800 microsecond. T is equal to 2000 microsecond. Okay, so T is nothing but your time period, okay, of your commutation cycle, you can see. So for a constant load current of 80 ampere, compute the following: effective on period, peak currents through main thyristor T1 and auxiliary thyristor TA, turn off time for thyristor T1, capacitor voltage 150 microsecond after TA is triggered. Okay, so one by one let us first find. So first thing is peak current through the main thyristor T1 and auxiliary thyristor TA. Yes, how it will be? Peak current through the main thyristor and auxiliary thyristor. Recall the voltage commutation circuit diagram. How it is, you can check. This is your voltage commutation circuit diagram. Whether this circuit we already analyzed or not. We have already analyzed na, right? So let me redraw this circuit again. Yes. This is thyristor T1. Here it is a capacitor. Here it is auxiliary thyristor. Here it is like a diode, inductor, freewheeling diode, and load. So this type of circuit we are having, and actually here we place the one resistor in order to charge the capacitor, right? When the circuit is at the rest position. Yes or no? Please check. Same circuit we have discussed in the chapter number 1. This is your main thyristor T1, capacitor C, auxiliary thyristor, diode D, inductor, freewheeling diode. This is R, L, and E, right? So how is the operation of this circuit? Yes, this is the voltage commutation circuit. Initially, this switch is closed. Capacitor go on charging. Okay, capacitor go on charging. Capacitor will be charged to the voltage of Vs volt. Na? So plus minus here, this is a Vs. Once capacitor charged, this switch is open. After that, at T is equal to 0, we turn on the thyristor T1. So once T1 turns on, current will be flowing like Vs, T1 load, and again back to the Vs. The load is highly inductive. Na? They have given I0 is equal to capital I0. They have given it is 80 ampere in this case. So current is flowing into this loop. So one current is in the outer loop. Second is this capacitor will try to discharge through this loop. Whether the capacitor will discharge in this loop, definitely, because your diode D will be in a conduction mode. Na? So capacitor, thyristor, inductor, diode, and again back to the capacitor. In this loop, the current will be flowing. So you can check this current is IT1. This current is IC. Na? This current is IC. We have drawn the waveform of IC and IT1. Okay, you can check. IC waveform is a sinusoidal. IT1 waveform is addition of this load current and this IC waveform. Okay, so how it is? I'm drawing here. I0 waveform is like this. We have already drawn. So this is your constant current load current I0. IT1, if you recall it, either you can say omega t or you can say t also, doesn't matter. Okay, so IT1, it is like a IC plus your I0. So this type of waveform we're having. This is IC plus I0. This is the I0. IC waveform, it is like this. Yes or no? Right? So capacitor discharges and again charges to the reverse polarity, na? Right? So IC sinusoidal means your VC will be co-sinusoidal. Okay. So how was the VC waveform? If you recall the VC waveform, it was like this. Capacitor discharges. Initially it is a Vs. After that it is discharging and again charging to the reverse polarity. Charges to the reverse polarity. This is a plus Vs. And this voltage is like a minus Vs. This voltage is like a minus Vs. No? So it is a co-sinusoidal waveform, right? So the same waveform we have discussed earlier. Let me draw these waveforms here, and so that we can find whatever the things they have asked. Okay. Yes. IT1 is there, IC is here, right? So after this instant, we are having okay. So this instant is like we indicated it with a T1. This instant is like a T2. Here we indicated it like a T3. Okay. Yes. T3. Right. This is a T1. Similarly, let me draw here. This instant is like your T1. Correct. After that, constant voltage, and next the linear shape. And again, it is a constant. This voltage is a Vs. This is a linear. This is a cosinusoidal. Yes or no? This is a linear. This is a cos. Why it is linear? We discussed it at that time also. Why it is linear? Because your capacitor current was constant here, right? Next, how is the waveform of V0? V0 waveform. It is like T1 here. Yes, this instant is like your T2, correct? And here it is a T3. 0 to T1, your Vs is a V0 is Vs. After that, it will be having this type of waveform. At this instant, what we done? Thyristor, main thyristor, that is a T1, is a turned on. So here T1 is on. At the small T1, auxiliary thyristor we applied gate signal. Na? So here it is TA is turned on. At the T is equal to T2, it is like, sorry, here actually not TA, we applied the gate pulse to TA at this instant, right? So here the TA is turned on, so T1 will be turned off. I will repeat how it operates again. Okay, so TA off here. So check here what is happening in the circuit. Okay, in short, I will summarize the circuit operation. So this is the circuit we are having. Initially, capacitor is charged to the voltage of Vs volt. With the help of this switch, we charge the capacitor. At T is equal to 0, thyristor T1, gate pulse is applied. So as soon as the gate pulse is applied to thyristor T1, what will happen? Current starts flowing from Vs, T1 load and again back to the Vs. Okay. So current is flowing from source to the load through the thyristor T1. Second thing, this capacitor which was initially charged, na, plus here, minus here, this capacitor will try to discharge here. Yes or no? This capacitor will go on discharging. So through the thyristor T1, we are having the two currents. One is the load current and second one is the discharging current of the capacitor. Yes or no? So here you can check thyristor T1 current IT1 is equal to IC plus I0. So that's why here you can check IT1 waveform is like this. I0 is your constant current. I0 is the constant current. Okay, I0 is a constant current. IT1 is equal to I0 plus this IC. Now, why the IC is sinusoidal? The same expression we have already derived. Please check the voltage commutation technique. you will understand the IC waveform, right? This is the IC waveform. It is a sinusoidal, and the expression we derived, it is a Vs under root C by L into sine of omega 0 t. You can check it, okay? So we're having the sinusoidal IC, right? So IC sinusoidal I0 constant. So addition of this waveform and this waveform is nothing but your IT1 waveform, okay? So it is like capacitor will discharge and again charges to the reverse polarity. So capacitor is discharging through the diode D, thyristor T1 and inductor, and again it charges to the reverse polarity. So you can check from t is equal to 0 to small t1. Voltage across capacitor will be changing from plus Vs to the minus Vs, and the nature is co-sinusoidal. So here we are having the voltage across capacitor waveform. Voltage across capacitor, it is plus Vs, here it is a minus Vs, right? Next, now what is the V0 during 0 to T1? During 0 to T1, if you check V0, that is nothing but the voltage across load. V0 is the voltage across load, is nothing but it is same as of the supply voltage now, because thyristor T1 is acting as a short circuit. So V0 is equal to Vs only, right? So V0 is equal to Vs we are having. So it is a Vs. This is a Vs, right? Next, this will continue till T1. At T1, sorry, from T1 to T2, from T1 to T2, it is like a capacitor has discharge and charge to the reverse polarity now. So voltage across capacitor polarity will be plus here, minus here, and the voltage is Vs now. So that's why you can check the Vc. It is a minus Vs. This voltage is now minus Vs. So from T1 to T2, the voltage across capacitor is the same, because for the capacitor, the discharging path is not available now, because we have not applied the gate pulse to auxiliary thyristor, right? So if the gate pulse is not applied to the auxiliary thyristor, then what will happen? This capacitor will not discharge. So that's why IC will be definitely 0. So you can check T1 to T2, IC is 0, right? Now what is the IT1? IT1 is nothing but only I0. That is only outer loop current will be flowing. Current will be flowing from source to the load through thyristor T1. So that's why your IT1 is I0, and again I0 is also constant current, okay? So T1 to T2, again the V0 will be same as that of the supply voltage, because thyristor T1 is in a conduction mode. So we're having, this is the T1 to T2, V0 is Vs again. At T2, we're applying the gate pulse to auxiliary thyristor. Here it is, auxiliary thyristor is turned on. So as soon as auxiliary thyristor turns on, means gate pulse is applied to auxiliary thyristor. Yes, it is like this capacitor will try to discharge in this loop now. So immediately a high reverse voltage will be maintained across the thyristor T1. So our thyristor T1 will turn off immediately. So thyristor T1 will turn off. So you can check thyristor T1 current. As soon as thyristor T2, the auxiliary thyristor gate pulse is applied, our thyristor T1 will turn off. So thyristor T1 current, that is IT1, will become suddenly 0. This is the thing we discussed in the voltage commutation. Na? Whereas in the current commutation, if you recall, the IT1 waveform, it is not having the sudden decrease 0, sudden change to the 0 value. In a current commutation, it is like capacitor was discharging, yes, and in that loop, yes, we had a inductor na. So that's why in a current commutation, if you check IT1 waveform, it was like decreasing slowly. But in this case, the IT1 waveform will suddenly fall to 0 value because of the high reverse voltage. So once your thyristor T1 turns off, once the thyristor T1 turns off, then what will happen? Then our capacitor will discharge through auxiliary thyristor, load, and again back to the Vs. In this loop, the capacitor will discharge. So when capacitor discharges in this loop, what is the capacitor current? You can check, it is I0 now. Capacitor current positive means it is upward direction. But actually when capacitor discharges, the current is flowing in this branch, it is a downward direction. So IC is equal to I0, but it is a negative, minus I0. Okay, so you can check IC waveform. It is a minus I0. So IC is constant. This is equal to minus I0. Now IC constant. So what about the VC? VC is linear, na? Right? VC is a linear. So that's why it is a linear. Initially it was IC sinusoidal, VC was cosinusoidal. Next T2 to T3, the IC is a constant value. So VC is 1 by C integration of IC dt na. So 1 by C integration of constant value is, it is like a T, time T, that is a ramp signal na. Integration of constant term is a T na. So it is a ramp signal. So that's why here we're having the ramp type signal, that is a linearly changing. Okay. And at T3, at T is equal to T3, at T is equal to T3, yes, capacitor voltage will reach the, at T is equal to T3, capacitor voltage will reach the Vs value. So Vs value means again it is a plus here and minus here. Okay. So once here it is plus, here it is minus. This capacitor will try to discharge through this path, but gate pulse is not applied to thyristor T1. capacitor will try to discharge through this path, but equal and opposite forces. So our capacitor will not discharge. So that's why here we'll be getting the, yes, waveform will be like this. Okay, and from T2 to T3 you can check V0 waveform. Simply apply KVL. Same thing we already done. Okay, because VC means what? During T2 to T3, V0 is nothing but your Vs plus Vc actually, right? So that's why we're getting this type of waveform. Here it is 2 Vs. It is changing from 2 Vs to the 0 value. 2 Vs to the 0 value, right? So this is the in short circuit operation. Same thing we already discussed. The only here I have summarized it in order to solve this numerical. Okay, so in this numerical now let us check the effective on period. Effective on period. Now effective on period means you can check this circuit we are using as a chopper. This circuit we are using as a chopper because you can check from here to here where the output voltage is a DC only. It is a positive voltage, and chopper means what? It is a DC to DC converter. And here you can check input is wherever input is DC and output we are getting, it is also DC na, right? And by changing the T1, T2, T3 instance, we can control the output voltage. So that's why they have referred it as a voltage commutator chopper circuit. Okay, so now what is the effective on period? Effective on period is nothing but yes, T1 to T3 period, that is T3 minus T1, T3 minus 0, T3 0 to T3 period, that is the effective on period, right? You can check in a DC to DC converter when switch is in a on state, it is like output voltage is a non-zero now, right? And again when off state, it is like output voltage is 0. So same type of concept we are having. So here from this point to this point, output voltage is a non-zero. So that's why effective on period is nothing but T3 minus 0, that is the T3 instant. Now in the T3 you can check, in the T3 you can check we are having 0 to T2. 0 to T2, T1 is on state or off state. Here it is T1 on. At this instant, T1 is turning off. So 0 to T2 is like your on time of the thyristor T1. On time of the thyristor T1. And T2 to T3. T2 to T3 is nothing but what? That is T3 minus T2. So in that also, if you check the circuit, we have indicated this instant as a circuit turn off time, na? TC for thyristor T1. So can I say that if this interval is your TC, then can I say that from this point to this point, it is like a double of that of this one. So it is like 2 times TC. Okay. So let me write effective on period. Effective on period or on time, you can say, is equal to T3, 0 to T3, that is T3 only, which is equal to, I'm writing it as a T2 minus, that is T2 minus 0, that is T2. T2 plus T3 minus T2. Now T2 is what it indicates. T2, that is the on time of the thyristor. Okay, on time of the thyristor. And they have given, you can check commutation circuit parameters. T on is 800 microsecond. That is the on time, okay, of the thyristor T1 is 800. So it is a T on. Plus T3 minus T2 is 2 times TC. 2 times TC. So here T on is, they have given it is a 800 microsecond, 800 into 10 to the power minus 6 plus 2 into what is a TC, circuit turn off time expression. We have already identified, we have already derived the expression for circuit turn off time of voltage commutation circuit. It is a C into Vs by I0 na, right? So it is C into Vs upon I0. How we have derived the TC expression? You can check during this interval, that is from this point to this point, this is a TC. So during TC, what we wrote during TC, IC is equal to I0. IC is equal to I0. Okay. So we use the expression IC is equal to C into dVC by dt. So in like that, we have derived the expression of TC. Okay. You can go back and check it. So it is 2 into C into Vs by I0. So it is 800 into 10 to the power minus 6 plus 2 into what is C value? 50 microfarad into Vs 220 volt divided by I0. It is a 80 ampere, right? 80 ampere. Yes, please check. This is equal to Yes, it is 1.075, right? Millisecond. Right? Yes. Why we have taken 2 TC means you can check now. Actually, your on time is from this point to this point. 0 to T2 is like your on time of the thyristor. And only thing is we need to add this time na T3 minus T2. In the T3 minus T2, you can check this instant from here to here. If this is TC means this is also TC na. And it is linearly changing from minus Vs to 0, whatever the time it has taken. So same time it will take na. So that's why it is TC means this is also TC. So that's why this is TC and here it is TC. Right? So that's why I have taken it is a 2 times TC. Yes or no? So it is 1.075 millisecond. Effective on period. Next. Peak currents through main thyristor T1 and auxiliary thyristor. Yes, what is the peak current through main thyristor? That is IT1 peak. And ITA peak. Yes, what is the IT1 peak? I0 plus IC peak na? I0 plus IC peak. What is I0? It is a constant and IC peak is Vs into under root C by L. So you can check it is a 80 plus Vs is 220 into under root C by L. What is the C value? 50 and L is 2 millihenry. 50 into 10 to the power minus 6 divided by 2 into 10 to the power minus 3. Yes, please check how much. $427.85, right? 427.85 ampere. No? What about ITA peak? What is the peak value of current flowing through the auxiliary thyristor? ITA peak. It is the same as that of the load current, na? Right? It is 80 ampere. Yes, 80 ampere. Next, turn off time for thyristor T1. That is a circuit turn off time. TC for thyristor T1. It is equal to C into Vs by I0. Na? It is 50 into 10 to the power minus 6 into 220 divided by 80. Please check it how much. We already discussed this circuit. Yes, it is 137.5 microsecond. 137.5 microsecond, right? And next, capacitor voltage 150 microsecond after TA is triggered. Yes. Now our task is to find the capacitor voltage 150 microsecond after TA is triggered. Okay, so you can check the circuit diagram, sorry, waveforms. TA is actually triggered at T is equal to T2. At T is equal to T2, capacitor voltage is like minus Vs, na? This is minus Vs. And this TC we know, they have asked the voltage across capacitor at 150 microsecond, na? At 150 microsecond. So you can check 150 microsecond after TA is triggered. TA is triggered at T2. So after this 150 microsecond, we need to check. After this means after this point, 150 microsecond we need to check. So what is TC? Just now we calculated TC value. It is a 137.5 microsecond. Okay. So if TC is 137.5 means this is 137.5. So 150 micro means somewhat here. Let us consider this is a this time interval from this point to this point. It is 150 microsecond. Na? Definitely it will be greater than TC. So it is a 150 microsecond. Now this time is 150 microsecond. And here you can check voltage is changing linearly. Voltage is changing linearly. So now our task is to find corresponding to this 150 microsecond, this instant, what is the voltage across the capacitor? Means this voltage we need to find. Let me indicate this voltage is VC dash. Let me indicate this as a VC dash. Okay. So now how to find this voltage? How to find this voltage? So you can check corresponding to this instant, corresponding to this interval, what is the current flowing through the capacitor? It is a I0. Current flowing through the capacitor is a I0. Yes or no? Right? Or you can simply use the slope. You can simply use the slope also. Doesn't matter. Okay. So how to find it? Let me write here. During TC, the dV by dt. During TC, capacitor voltage, that is VC, changes from minus Vs to 0. Minus Vs to 0. Yes or no? During TC, how the capacitor voltage is changing? It is changing from minus Vs to the 0. So what is dVc? dVc is equal to, yes, therefore dVc, let me write divided by dt is equal to 0 minus of minus Vs divided by dt is nothing but TC. Change in the time is TC. Change in the voltage is minus Vs to 0. So final value minus initial value. So it is a Vs by TC. Vs by TC. So now can I write it as Vs? We know it is a 220. And what is the TC? TC is, we have calculated it as 137.5 microsecond. Right? So this is actually volt per second. Okay. So we'll be getting it as equal to somewhat 220 divided by 137.5. 1.6 into 10 to the power 6 volt per second. This is actually the slope. This is actually the slope of your VC waveform. Slope of the VC waveform. Now our task is to find the 150 microsecond. After the 150 microsecond, so you can check here in this waveform. This total is 150 microsecond. TC we know. TC is equal to 137.5 microsecond. So can I write this instant means this time total, that is 150 micro minus TC means remaining time is, let me indicate it as, can I indicate this time? Only this time I am saying. Yes, this time is like 150 micro minus TC na. 150 micro minus TC. So if you check, it is equal to 150 minus, what is TC? 137.5. So it is 12.5 micro. Right? So means only corresponding to 12.5 micro, what is the value of this VC we need to find? Because it has reached from minus Vs to 0 here. At this instant, it is 0. After that, it is changing or it is increasing into the positive values. Okay. So if I put here 12.5 microsecond, if I put this T here, if I multiply this term with a 12.5 microsecond, I will be getting the VC waveform, that is VC dash value. Okay. So therefore, VC at or after 150 microsecond, 150 microsecond. Yes, VC after 150 microsecond after TH triggered. Okay, VC 150 microsecond after TH triggered. After TA is triggered. So is equal to your 1.6 into 10 to the power 6 into 12.5 into 10 to the power minus 6. So it is equal to 12.5 into 1.6. So it is a 20 volt. 20 volt. So VC voltage is equal to 20 volt. Okay, VC voltage is equal to 20 volt. Is this clear? Simply I have used right, it is a 20 volt. Simply I have used this slope, right, and corresponding this time. Okay, so or you can use IC is equal to C into dVC by dt expression also, doesn't matter, you will be getting the same answer, right, like that also. So this is about the second numerical. Next, the last numerical we'll discuss. Yes. Yes. A voltage commutated chopper operating at 1 kilohertz is used to control the speed of DC motor as shown in figure. Same voltage commutated chopper we are having. The load current is assumed to be constant at 10 ampere. The minimum time in microsecond for which the SCRM should be on is. Okay. So our task is to find the minimum time for which this SCRM should be turned. It should be in an on state. Now, how to find the minimum time for which SCRM should be on? The meaning is you can check in this circuit. Definitely, initially capacitor will be charged to the voltage of 250 volt, like the polarity plus here minus here. As soon as the gate pulse is applied to that SCRM, our SCRM will turn on. Current will flow from supply voltage M load and again back to the supply, right, in this loop. Second, capacitor go on discharging. So you can check after omega 0 t is equal to pi, right, omega 0 t is equal to pi, because capacitor waveform we are having like this. It is a sinusoidal, no? So this type of IC we are having. So this instant is like this is a pi, na? So this time is nothing but pi by omega 0. Pi by omega 0, this time. So now suppose at this same instant, if we apply the gate pulse to the auxiliary thyristor, and during this instant, what is the VC? VC is like capacitor discharging and charges to the reverse polarity, na? Capacitor discharges and charges to the reverse polarity. So corresponding to this instant, the voltage across capacitor is minus Vs. This is a minus Vs. Here it is a plus Vs. Plus Vs, here it is a minus Vs. Now, at this instant, if I apply the gate pulse to the auxiliary thyristor, then what will happen? Immediately our main thyristor will turn off, right? So the minimum time in microsecond, the meaning is this time indicates your minimum time, okay, minimum time for which our SCRM will be in on state. Whereas if you check in the previous case, this instant is like T1. In a previous case, we considered this instant is like T1. You can check. In the previous case, we considered this instant like a T1, right? This instant is like a T1 we considered now. And we applied the gate pulse to auxiliary thyristor after this instant, means we have kept yes, from T1 to T2 the auxiliary thyristor is not in a functioning mode. We have applied the gate pulse to auxiliary thyristor at T2. You can check at T2 we have applied the gate pulse to auxiliary thyristor, but they have asked the minimum, time. The meaning is if I apply the gate pulse to auxiliary thyristor at this instant only, then immediately my thyristor M will turn off now, right? So that's why here the minimum time in microsecond for which SCRM should be on is nothing but your pi by omega 0 time only. Pi by omega 0 time only, right? So let me write minimum time for which SCRM yes is on. Okay, SCRM is in an on state is equal to pi by omega 0. Omega 0 is 1 by root LC, na? So it is equal to pi into root LC. So it is pi into under root L into C. What is the L? 2 milli and 1 micro. C is the 1 micro. 2 into 10 to the power minus 3. 1 into 10 to the power minus 6. Right. So please check how much. pi into root LC, right? (140 micro, right? 140 microsecond. Okay, so 140 microsecond. Next, the second bit, the average output voltage of the chopper will be. Okay, so our task is to find the average output voltage. So average output voltage is equal to your on time divided by total time into the supply voltage, Okay, so let me write here V0 average, because it is behaving as a chopper. Average output voltage. Yes, it is equal to T on divided by T into your supply voltage Vs. Okay, into supply voltage Vs. So now what is T on? In the previous example, we indicated the T on. What is the T on? It is the on time of the thyristor plus 2 times Tc, na? Right? So it is a T on is nothing but T on plus 2 Tc. Please try to understand this. This T on means what? On time of a thyristor plus 2 times Tc. Okay, or let me write as T on dash divided by T into Vs. What is T on here? That is the instant during which thyristor is in an on state. Okay, so if you check, our thyristor is in an on state only for pi by omega, that is pi into root LC. Okay, so it is pi into root LC plus 2 into Tc divided by T into Vs. So it is pi into under root L into C, 2 milli into 1 micro. Divided by how to find the T, they have given it is a 1 kilohertz frequency. So it is 1 upon 1000 into Vs. Vs is 250. Yes, please check how much. Yes, it is like a step down chopper only, because during T on plus 2 Tc output voltage is non-zero, and during that instant till your capital T completes, it will be 0 again. Okay, yes, 2 Tc term is the same thing we discussed here. Why I have added this 2 Tc? Yes, it came from this waveform, na? This is Tc plus this is Tc, so that's why T2 to T3, this is like your 2 Tc, na? So this is your on time of the thyristor, main thyristor, plus 2 Tc, that is nothing but your full on time. And where will be your capital T now? The capital T will be somewhat here. This is time T, capital T will be suppose somewhat here. And from T3 to T capital T, it will be 0 again. And after this capital T, again the same waveform will repeat, na? So it is like a periodic time is capital T, and on time is 0 to T3. So how we have calculated 0 to T3? It is like this time plus this time, na? So it is this time plus this time. What is this time? This time is like time during which your main thyristor is in on state. And this time is like Tc plus Tc, na? That is 2 Tc. So that's why here that is on time of the main thyristor plus 2 Tc. Okay, that is nothing but, yes, here it is. Yes.
Sir, just one thing, sir. For time T2 till T2 plus 2C, the voltage is actually greater than Vs, no, sir?
T2 to
T2 plus Tc. So then in that case, then how can we use this Buck expression, sir? dVs.
Where you are saying T2 to
T2 plus TC till this point, this midpoint.
T2 plus TC.
In V0 waveform, sir. From T2 to T2 plus TC, we have voltage greater than Vs.
So what?
So we can use buck, like for that period, we can use buck expression, sir, for the entire period.
Yes, na, because the thing is here we are in the on period. During this, the output voltage is non-zero.
Okay, sir.
This is your overall period.
Okay.
Right?
Okay, sir.
Okay. So, or you can check now if you want to find the V0 average, na, you can find this area plus this area also.
Okay, sir.
Right? Doesn't matter.
Okay.
Okay. Yes. Yes. What is the answer? $35 or 47? T value is 1 by frequency. Right? 47.6, na? Okay. So, if you want, either you can find, yes, this is the V0 average of the area under this plus area under this. Okay. And that is area under this plus area under this divided by your total time T. That will give the V0 average. Or you can check here. This is 2 Vs, this is 0, na? So what is the average of this T2 to T3? Again, it is a Vs only, na? Right? So directly I have taken it as this time into this Vs divided by this entire time. Right? In both the ways, you will be getting the same answer. Here TC value is okay, plus 2 TC I have not taken. Okay. Divided by this term plus 2 into TC, na, that is 2 into C into Vs divided by I0. TC means C Vs by I0. For voltage commutation circuit, what is the TC? C Vs by I0. Right? Okay. Sir, why we are taking pi by omega 0? Yes, pi by omega 0 means this instant where your SCR-M conducts, and at this instant if the thyristor TA is turned on, so what will happen? Immediately your main thyristor turns off. Okay, and capacitor voltage will be linearly changing. So like this will be getting the capacitor voltage, right? Means whatever in the previous case we had the time interval, na, from T1 to T2 time interval. Yes, this T1 to T2, that is T2 minus T1. In whatever the example right now we are discussing, in that case T2 minus T1, this time will be 0. Means indirectly this pulse will appear here, right? Immediately your thyristor T1 current will fall to 0. Means this constant pulse will not appear. Okay, because they asked the minimum time, na? They asked the minimum time, right? So it is like at this instant we applied the gate pulse to thyristor. Okay, so like this. Yeah. So this is about the numericals related to the voltage commutation and current commutation chopper circuits. Next, now let us discuss the types of the choppers based on quadrants of operation. Okay, types of choppers based on quadrants of operation. A small theoretical bit is there. Types of choppers based on quadrant of operation. Actually, we are having 5 types: type A, type B, type C, type D, and type E chopper. Okay, so let us discuss one by one which are those types. Okay, and how is their circuitry. Okay, so far they haven't asked the question. So first, type A chopper. It is a single quadrant chopper. Type A and type B, these are the single quadrant choppers. Type C and type D, these are the 2 quadrant choppers. And type E is a 4 quadrant chopper. Okay, so type A chopper, let us first discuss. It is a single quadrant chopper. Okay, so type A chopper is like your step down chopper only. It is like a step down chopper only. This is a VS switch diode D or freewheeling diode, you can say. This is a load. Suppose the switch is S1 and let me indicate the diode is a D1. Okay, so next V0, let me indicate I0, S1 and it is D1. Okay, so here this is a simple step down chopper. We already discussed. When S1 is in a on state, it is like a current will flow from VS, S1 load and again back to the VS. Right? In this loop, the current will be flowing. Okay. So the load, right? Generally, here we are going to consider the load is either RL load or RLE load. RL load or RLE load. Basically, these types, type A, B, C, D, E, these are used for DC motor drives. DC motor drives. Okay. So when S1 is in on state, current is flowing from source S1 load and again back to the VS. In this loop, the current will flow. The load inductor go on storing the energy. So what is the load voltage? This is the load voltage V0. This is the load current I0. So you can check when S1 is in on state, current is flowing from source to the load. So what is I0? Positive or negative? I0 is a positive only, na? Right? So I0 is a positive. When S1 is in on state, I0 is positive. Similarly, what about the V0? When S1 is in on state, V0 is equal to Vs. Can I say? Yes, because S1 is a short circuit. So V0 is equal to Vs. So Vs means it is again positive. So when S1 is in on state, we are getting the V0 positive, I0 also positive. Okay. Next, so it is like load inductor has stored the energy. Load inductor has stored the energy. Next, when S1 is in an off state, what will happen? This load inductor will oppose the change in the current. So whatever the energy stored by the load inductor, it will release through the diode D1. Means when S1 is in off state, diode D1 starts conduction. Okay. So here when inductor releases the energy through the diode D1, what is the I0? Positive or negative? Inductor will release the energy in the same direction, na? Right? So therefore I0 is a positive only. I0 is a positive. What about the V0? You can check the load voltage is nothing but the voltage across the conducting diode. So when diode D1 is in a conduction mode, V0 is equal to 0 volt. So here voltage V0 is either 0 or positive. Current is always positive. So V0 is either positive or either 0 or positive, and current is a positive. So here we are having the I0 axis. This is the V0 axis. Okay. So you can check for this circuit, when S1 is in on state, V0, I0 positive. And when S1 off, D1 conducts, V0, I0 is positive, V0 is 0. Means what? Yes, the quadrant of operation is the first quadrant. You can check. In the first quadrant, V0 is positive, I0 is positive. Yes or no? So that's why this chopper operates in the first quadrant. Okay, simple. Next, so this table, right, it explains when S1 on, what will happen? When D1 on, what will happen? D1 is the uncontrolled switch now, right? So it will turn on when inductor releases the energy. Next, let me write the type B chopper. Type B chopper. This is generally used for regenerative braking, type B chopper. This is diode D2, suppose switch is S2. R, L and E. This voltage is V0, right? And current we consider it is a I0, right? So S2, V0, I0, D2, V0, I0. Okay. Yes. So when S2 is in a on state, when S2 is in a on state, what will happen? Current will flow from ELR and again back to the S2. Yes or no? In this loop, the current will flow ELR, S2 and again back to the E. In this loop, current will flow, right? So now we can check when S2 is in a on state, current is in the upward direction in this branch. So I0 is positive or negative? I0 is negative. Yes or no? It is like your load inductor go on storing the energy. Load inductor go on storing the energy. So here I0 is a negative and load inductor is storing the energy. So what will happen? S2 is in on state, load inductor stores energy and voltage across the short circuit branch, that is the S2 is equal to 0. So your V0 is equal to 0 now, right? So V0 is equal to 0 volt and here I0 is a negative. I0 is a negative. Inductor stores energy. Let me write when S2 is in on state, inductor L stores energy. Stores energy. Next, when S2 is in a off state, when S2 is in a off state, it is like inductor will oppose the change in the energy. So that's why inductor will, yes, reverse its polarity, because when S2 on state, polarity of the voltage across inductor is like plus here, minus here. Na? Next, when S2 is in off state, polarity of the voltage across inductor is reversed. So you can check inductor polarity, inductor voltage polarity and E polarity. These will be adding, na? Right? And this voltage will be, if this voltage is greater than that of the Vs, then the current will flow like E, L, R, D2 and Vs. In this loop, the current will flow. Means when S2 is in an off state, current will flow from load to the source. Current will flow from load to the source. Okay. So that's why it is a braking, regenerative braking. Okay. So here you can check when current is flowing into this loop, what is the I0, positive or negative? I0 is a negative. What is the V0? V0 is equal to Vs na? So V0 is positive, I0 is a negative. Okay. So I0 negative, V0 positive. That is the Vs. Okay. So you can check here in this chopper. Okay. I0 is a negative only and V0 is a positive or 0. So V0 positive or 0, I0 negative. Okay. So what is the quadrant of operation? Quadrant of operation will be second quadrant. You getting the point, right? S2 on state, inductor stores energy. S2 off state, yes, current will be flowing from load to the source, right? So second quadrant operation. Next, we're having a type C chopper. Type C chopper is a combination of type A and type B chopper. Okay, type C chopper. It is also known as two quadrant type A chopper or two quadrant type A chopper. Type A chopper. So here, two quadrant type A, I'm saying. I'm not saying directly type A. It is a two quadrant type A. Okay, so circuit diagram. right? This is supply voltage Vs. Switches are S1, S2, diodes are D2 and D1. Okay, so yes, so V0, I0, let me write S1, D1, S2 and D2. Okay, so first, when S1 is in a on state, V0 means this voltage and I0 means this current. Okay, so when S1 is in a on state, current will flow from Vs, S1 load and again back to the Vs. In this loop, the current will flow. What is I0, positive or negative? I0 is a positive. And what is V0? V0 is equal to Vs. That is again positive. Okay, so I0 positive, V0 also positive. Okay, it is like inductors go on storing the energy. Inductor go on storing the energy, right? When S1 is in a off state, when S1 is in a off state, inductor releases energy through diode D1. Inductor releases energy through diode D1. Okay, in opposite to that of the your EMF E. So when inductor releases energy through diode D1, what is the V0? V0 is a 0. What about the I0? I0 is a positive. So I0 positive, V0 0. Next, when S2 is in a on state, current will flow from E, L, R, S2 and again back to the E, like this. In this loop, the current will flow. Load inductor go on storing the energy, just like your type B chopper. Okay, so when S2 is in a on state, I0 is a negative. We will be getting I0 is negative, right? And I0 negative, V0 is a 0 na, voltage across short circuited S2. So it is a 0. Load inductor stores energy. When S2 is in an off state, inductor reverses its polarity in order to oppose the change in the current, that is in order to release the energy. Okay, so therefore VL and E will be adding now. So current will flow from load through D2 Vs and again back to the load. Means current is flowing from load to the source. Current is flowing from load to the source. So what is V0? V0 is equal to Vs. I0 is a negative. Okay, so we are getting I0 is a negative and V0 is equal to 0. So we can check here. Yes, sorry, V0 is equal to Vs. V0 is equal to Vs, right? Current is flowing like this now. So V0 is positive. V0 is positive. So you can check the quadrant of operation. Yes, quadrant of operation. This is a I0 and this is a V0, right? We're getting I0 positive as well as negative. Okay, and the V0 is only positive, right? So quadrant of operation will be like this. First and the second quadrant. First and the second quadrant, right? Next, type D chopper. It is also known as two quadrant type D chopper. Two quadrant type B chopper. Right? Two quadrant type B chopper. So S1, S2, D2, D1, and it is load. Right? Voltage across load V0. Current from the load I0. Right? So S1 S2 D1 D2 S1 D2 and S2 D1. Right. So when S1 and S2 are in a on state, how the current will flow? Current will flow from source towards the load, na? Right? V0 is a positive, I0 is also positive. Okay, so V0 positive, I0 positive. So positive, and here it is also positive. It is like a inductor go on storing the energy. Load inductor go on storing the energy. After that, when S1 S2 are in a off state, it is like inductor will release energy through diode D1 D2 in opposite to that of the supply voltage. So it is like inductor releases the energy. Okay, so now here, in order to get this, either we need to reduce the value of supply voltage, or whatever the back EMF is there, okay, in the load, we need to reverse the polarity of that back EMF, so that L and E will be getting added. Then and only then your current will flow from load to the source. Otherwise, it is not possible. Okay, so it is like current is flowing from load D2 Vs D1 and again back to the load. In this loop, the current will flow. So if the current is flowing into this loop, what is the V0? V0 is equal to minus Vs. I0 is positive. So I0 positive, V0 is negative. Minus Vs means it is negative. Next, suppose either this is, that is either through the load, or suppose already we are having RLE here. Okay, and current, suppose S1 is in an on state, then current will flow like a load D2 S1 and again back to the load in this loop. Okay, means current is flowing from E we are here keeping like this, right? So E D2 S1 load and again back to this. In this loop, the current will be flowing. Okay, so V0 is 0, I0 is positive. So V0 0, I0 positive, right? And second, it is like inductor stores energy. And after that, if S2 is in an on state, then it is like inductor will go on releasing the energy in this way. So D2 V0 is 0 volt, I0 is a positive, I0 is a positive. So we'll be getting current is always positive, voltage is positive or negative. Okay, voltage is positive or negative, current is always positive. These are conditional operations only, right? I0 V0. V0 positive or negative, and I0 is positive only. This is the type D chopper, and the last one, type E chopper. It operates in 4 quadrants. 4-quadrant chopper. Four-quadrant chopper. Okay, so we're having a supply voltage Vs, load is a RLE load, S1 S2 D1 D2 S3 D3 S4 D4. Okay, this is a load. This voltage is V0 and current here is a I0, right? So Okay, so when S1, S2 are in a on state, that is when S1 is in on state, S2 is in on state, current will flow from Vs, S1, load S2, and again back to the Vs. In this loop, the current will flow. So inductor go on storing the energy. V0 is equal to Vs, I0 is positive. I0 positive, V0 positive. I0 positive, V0 is a positive. When S1, S2 are in off state, when S1, S2 are in off state, okay. So what will happen? Yes, inductor will go on releasing the energy through load D3, Vs, D4, and again back to the load. In this loop, the inductor releases energy. Okay. So when inductor releases energy in this loop, you can check what is V0. V0 is equal to minus Vs. You can apply KVL. You will be getting V0 is equal to minus Vs. I0 is positive. So V0 is negative. I0 is a positive, right? I0 is a positive. Next, when S3, S4 are in a on state, current will flow from Vs, S3, load S4, and again back to the Vs. In this loop, the current will flow. Vs, S3, load S4, and again back to the Vs, right? In this loop, current will flow. So what is V0? V0 is negative. I0 is also negative, na? Current is flowing like this. V0 and I0 both are negative. So, okay. This is when S1, S2, na? Correct. Yes. This is V0 and I0. It should be like this, na? This is positive, positive. S1, S2 we discussed, na? And next negative, positive, na? Yes. Next, what will happen? Let us discuss. Okay. So when S3, S4 are in on state, current will flow like Vs, S3, load S4, and again back to the Vs. In this loop, current will flow. What is I0? I0 negative, na? You can check in this branch, current is from right to left. So I0 is negative. What about the V0? Negative of the load is connected to the positive of the supply. Positive terminal of the load is connected to the negative terminal of the supply. So your V0 is also negative. V0 negative, I0 negative. Load inductor go on storing the energy now. After that, when S3, S4 are turned off, S3, S4 are turned off. Yes, load inductor releases the energy like load D1, Vs, D2, and again back to the load. In this loop, the current will flow. So if you check when the current is flowing into this loop, what is I0? I0 is negative and V0 is positive because positive is connected to positive, negative is connected to negative. Okay. So I0 negative, V0 positive. So you can check V0, I0 positive, V0 negative, I0 positive, S3, S4 on, V0, I0 both are negative, and here V0 positive, I0 negative. Okay. So the quadrant of operation, it operates in all the four quadrants. So this is a I0, this is a V0. Right. So V0 is positive, negative, and I0 is also positive and negative. Right. Again, this is not the unique operation. This is not the unique operation because in some of the books, if you check, they have given like S1, S2 on state. After that, S1 is turned off. Then inductor releases energy through D2, S2, D4 also. Like this also they have done. This is also possible. Okay. That's why I told you this is not the unique operation. Okay. But we can achieve the four quadrant operation. We can achieve the four quadrant operation. Right. So you can recall in the drive we're having the four quadrants: forward motoring, forward braking, reverse motoring, reverse braking. Okay. So if we use the type E chopper, then for the DC motor, we can control in any of the quadrant, right? Forward motoring, reverse motoring, forward braking, and reverse braking as well. Right. Okay. So this is about the DC to DC converters. Now we are going to discuss the next chapter, that is DC to AC converters. Okay, inverters, DC to AC converters, that is the inverters. Yes, let me put the heading DC to AC converters. It is also known as inverters. In this chapter, we are going to discuss the types of the inverters, just like a single phase half bridge, single phase full bridge with R load, L load, RL load, RLC load. Okay. Next, the three phase inverters, 180-degree conduction mode, 120-degree conduction mode, and pulse width modulation techniques, single pulse, multiple pulse, and sinusoidal pulse width. Okay. So, yes. So inverters, strictly speaking, it is the circuitry which converts fixed DC to variable AC. It is a static circuitry which converts fixed DC to variable AC. Fixed DC to variable AC converter. So variable AC means it gives the output in terms of variable voltage and variable frequency. Variable voltage and variable frequency. Variable frequency, right? Okay. So now where the inverters are used, you can check in the HVDC transmission at the receiving side, right? We use the inverter. In the facts, if you recall, in the reactive power compensation, we use the inverter. In the active filters, we use the inverter. In AC motor drives, we use the inverters. Okay, so these are the few applications of the inverters. So let me highlight applications. Yes. In that.
Yes, sir.
Yes.
Sir, previously some questions are we can found in previous gate question that what type of switching, that is feedback diode, or that diode is connected with the series. That questions are actually important for today's gate syllabus.
Feedback diodes are required here in inverters.
Yes, sir. But in a different circuit also we can DC to DC converter also we can use. What type of switches actually use? This type of question is important actually. Means
Okay.
according to load.
We will discuss at the end. We will discuss at the end, right?
Okay.
Okay. Yes.
Important, sir.
Okay. Yes. Whatever you want to say, we'll discuss it at the end, right? Okay. So applications, it is used for AC motor drives. Next, as long as your facts considered, it is used for active filters. Next, reactive power compensation. Next, HVDC transmission. Suppose I want to feed the power of solar, okay, solar plant to the AC system, then I need to use the inverter, right? So like this, we're having the number of applications of the inverter. Now let us discuss the types of the inverters. Types of inverters. So based on nature of input. So based on nature of input, there are two types. First one is voltage source inverter. That is a VSI. And second one is current source inverter. Current source inverter. VSI and CSI, right? So the difference between the two is, in a voltage source inverter, the input voltage is constant. That is, the input voltage to the inverter is a constant. Whereas in a current source inverter, the input current to the inverter is constant. Okay, so please try to understand the difference between the two. In the voltage source inverter, we are having the input voltage to the inverter is constant. Whereas in current source inverter, we are having the input current to the inverter is constant. Okay, so next. The second classification is, yes, second classification is based on nature of output waveform. Nature of output waveform. So we are having square wave inverter. Second, quasi square wave inverter. And third one, PWM, that is a pulse width modulated. Okay, PWM inverters. So these are the classifications based on the nature of output waveform. Square wave means it is like a 180-degree square wave. Let me show here. Square wave means the waveform of output voltage, it will be like this. This type of waveform. This is your square wave inverter. Okay. Next, quasi square wave means this type of waveform will be getting. It is having in between the zero intervals, right? This is a quasi square wave. We already analyzed a quasi square wave also. Yes or no? Where we got this quasi square wave? At the input supply current. Yes or no? Input or source current. Right? In the case of your RL load and with freewheeling diode, we got this type of waveform. And RL load without freewheeling diode, yes, that source current waveform, it was a square wave waveform, right? So this is a quasi square wave. And pulse width means it is again depends on which type of pulse width modulation we are using, whether we are using the single pulse, whether we are using the multiple pulse, or we are using the sinusoidal pulse. Okay. So at the time of PWM techniques, you will understand what is the PWM. Okay. So next, the third one is, yes, classification based on connection. Based on connection. Based on connection, right? So we're having a bridge inverter, series inverter, and parallel inverter. In the bridge, again, there are two types, half bridge and full bridge. Half bridge and full bridge. Half bridge and full bridge, right? Yes. Is my screen is not visible? Please check. Visible, no? Right? Okay.
Visible, sir.
Visible, no? Right. Okay. Yes. I think the slide number was not visible. That's why they are saying. Okay. Yes. Okay. Okay. So these are the classifications of the inverters. So now we are going to start with the very first inverter circuitry, that is the half bridge inverter, right? We'll discuss the half bridge inverter. So my question is, first of all, suppose if I go into the market and if I purchase the inverter, for example, suppose single phase inverter I have purchased, what should be my expectations from that inverter? Please listen the question. Suppose I go into the market and if I purchase the inverter, single phase inverter, what should be my expectations from that inverter? Come on. Yes, very good, Imtiaz. It should be inverter should give the pure sinusoidal waveform, right? Yes. Someone, Shubham, is saying low cost. Okay, obviously low cost is also required. Okay. Output should be pure sinusoidal. Good, good. Yes, pure sinusoidal, fixed voltage and frequency. Okay, anyway, right? So now as long as your single phase inverters are considered, the requirement, okay, is like that the output of the inverter should be a pure sinusoidal, means our inverter should give the pure sinusoidal output voltage, pure sinusoidal output voltage. But now let us discuss whether really our inverter is giving the pure sinusoidal or not. Okay, let us discuss. So let me put the heading single phase half bridge voltage source inverter, right? It is a single phase half bridge voltage source inverter. In the connection, it is a half bridge, that is a bridge inverter. And in the CSI and VSI, it is a voltage source inverter. Okay, so now let me draw the circuit diagram. Yes. This inverter requires a specially designed 3-wire DC supply. Okay, specially designed 3-wire DC supply. Suppose the load is purely resistive. Let me write the R load. Vs by 2, Vs by 2, this is a R, V0, I0, S1, S2, D1, D2, right? Current here, consider it is a IS1, ID1, ID2, IS2, right? So the waveforms generally in inverter, okay, because input is DC, right? So thyristors or SCRs are not preferred, because if we use the SCR, we need to give the forced commutation technique, means additional circuitry is required to turn off that SCR. Okay, so that's why generally which switches we prefer the MOSFET. Generally, if you check in real life, in industry, the output voltage frequency of the inverter is generally in kilohertz. Okay, it is in kilohertz. So if you check, if the output frequency required is kilohertz, the meaning is the switches which are having the high switching frequency, okay, are generally preferred. And we are having the MOSFET, right? We are having a IGBT, right? These are the switches where these are the fully controlled switches, and the output or the switching frequency is also high. Okay, so in most of the circuits, if you check, generally the MOSFETs are preferred in the inverter. So let me indicate here the gate pulse, or you can say the controlling signal. Let me indicate it as a IG. Please consider this IG is nothing but the controlling signal. Okay, so T by 2, this is a T, and 3T by 2. T by 2 to T. right? Okay, so this is T by 2, this is T, and this is 3T by 2. Okay, so, right? So now how to select this time T? Suppose I want to design the inverter, then how to select the time T? For example, suppose for domestic application, okay, you might have heard about the luminous inverter, okay, our very famous cricketer Sachin Tendulkar is advertising it, okay. So in the domestic inverter, what should be the output frequency? It is a 50 hertz in India. So if output frequency required is 50 hertz, that is a F is equal to 50 hertz, means our inverter should complete 50 cycles in 1 second, okay. So what is the time corresponding to 1 cycle? It is a 1 by 50, right? So 1 by 50, that is your 0.02, okay. So this time T is nothing but 0.02, because you can check corresponding to this time T, our inverter is completing 1 cycle, right? So this time T depends on the output frequency of the inverter, right? So yes, correct. Okay. Yes. So now let us discuss the circuit operation. Here we are having the circuit. Total input voltage is Vs only, but it is divided as Vs by 2 and Vs by 2. So it requires a specially designed 3-wire DC supply. I am saying 3 wire. This is the first wire. Here it is second wire. Here it is a third wire. Total input voltage is Vs. It is divided as Vs by 2 and Vs by 2. We are using two switches, S1 and S2, and the two diodes D1 and D2 here, right? Next, the load is purely resistive. Voltage across load is said to be positive. Polarity is plus here, minus here. Current is flowing from right to left. That is the positive direction of the current. Current flowing through the switch S1 is IS1. Current flowing through the switch S2 is IS2. Okay, this is ID1 and here it is ID2. We're having IZ1, IZ2. IZ1 is nothing but the controlling signal, okay, applied to the switch S1. IZ2 is the controlling signal which is applied to the switch S2. So here at T is equal to 0, we're applying the gate pulse 2, that is nothing but controlling signal to switch S1. Now the nature of controlling signal, it depends on which switch we are using. If we are using MOSFET, definitely the controlling signal is nothing but your VGS voltage na. If we are using the BJT, then our controlling signal is nothing but the base current, right? So nature of the controlling signal, it depends on the type of the switch or which switch we are using, right? Next, so at T is equal to 0, we are applying the controlling signal to the thyristor to the switch S1, and at T is equal to T by 2, we are removing the controlling signal. The meaning is our switch S1, okay, we are keeping it in on state from 0 to T by 2. At T is equal to T by 2, yes, we are applying the controlling signal to the switch S2, means we are interested in turning on switch S2 at this instant, okay. And at T is equal to capital T, we are removing the controlling signal, means at T is equal to capital T, our switch S2 will turn off. Similarly, again at T, we are applying the controlling signal to the switch S1, and again at 3T by 2, we are turning off the switch S1 and turning on the switch S2, okay. So here we are having, when S1 conducts, then S2 will off state, S2 conducts, S1 will be in off state, like this, okay. So now let us discuss the circuit operation. For T is equal to 0 to T by 2, for T is equal to 0 to T by 2, let me write, for T is equal to 0 to T by 2, switch S1 is in a on state, switch S1 is in a on state. So when switch S1 is in a on state, means it is like acting as a short circuit. How the current will flow? Current will flow from Vs by 2, S1 load, and again back to the Vs by 2. In this loop, the current will flow, right? So equivalent circuit will be like this. Let me draw in short. S1 is in a on state. This is Vs by 2, and here it is a load resistor R. This type of circuit will be getting. This is a V0, and here it is a I0, right? This is S1. This current is IS1. This is Vs by 2, okay. So only in this loop current will be flowing. So only in this loop the current will be flowing when S1 is in an on state, okay. So when S1 conducts, current will flow from Vs by 2, S1 R, and again back to the Vs by 2. So you can check voltage across switch S1 will be 0, right? So can I say that, or apply KVL? It is plus Vs by 2 minus V0 is equal to 0. So V0 is equal to Vs by 2. So let me write V0 is equal to Vs by 2. What about the I0? Load is purely resistive. So I0 is equal to Vs by 2R. That is V0 by R. Okay, Vs by 2R. So now we are having 0 to T by 2. S1 is in a conduction mode. So that's why V0 is equal to Vs by 2. I0 is equal to Vs by 2R. Right? At T is equal to T by 2, we are turning off switch S1 and we are going to turn on the switch S2. We are going to turn on the switch S2. So at T is equal to T by 2, S2 is turned on. So current will flow from Vs by 2, load S2 and again back to the Vs by 2. In this loop, the current will flow. So when the current is flowing into this loop, you can check, actually the loop current is clockwise, but in the resistive branch, that is the load branch, the current direction is from left to right. Means our I0 is negative here. Be careful. I0 is a negative. Okay. So now in this case, if you check, if you apply KVL, it is like plus Vs by 2 plus V0 is equal to 0. Okay. Plus Vs by 2 plus V0 is equal to 0 means V0 is minus Vs by 2 now. Right. So let me write for T is equal to T by 2 to capital T. Switch S2 is in a on state. S2 is in a on state. Okay, so V0 is equal to minus Vs by 2. And what is the I0? I0 is equal to minus Vs by 2 divided by 2R. Okay, so we're getting V0 and I0 both are negative. So we're getting V0 is negative, I0 is also negative. It is a minus Vs by 2, it is a minus Vs by 2R. Right? Next, again at T, we are again turning on switch S1. So again, this same cycle repeats, same cycle will repeat here. Okay. You can check input is your DC. Output, whatever we are getting, it is a, definitely it is not a sinusoidal, but it is a AC na positive, negative, means it is a AC. Output nature is, it is a square wave. Okay. So single phase half bridge inverter is a square wave inverter. It is a square wave inverter. Please try to understand. Okay. So now this is the V0 waveform and the I0 waveform. Now, if I want to draw the IS1 waveform and IS2 waveform, how it will be? IS1 waveform and IS2 waveform, if I want to draw, how it will be? Yes. Zero to T by 2 and T by 2 to T. Okay. And IS2 waveform. T by 2 and it is T. Yes, you can check S1 is in on state only from 0 to T by 2 na, and during 0 to T by 2 your IS1 and I0 both are same na, because current is flowing only into this loop. So IS1 and I0 both are same. So IS1 value is equal to I0 value. So it is equal to Vs by 2R. So the waveform will be like this. It is a Vs by 2R. Yes or no? T by 2 to T, what about IS1? T by 2 to T, IS1 0 na, because S1 is in off state. So here IS1 is 0. After T, again it will be same as that of the this Vs by 2R, right? So same cycle repeats again. What about the IS2? During 0 to T by 2, S2 is off state. So it is 0. T by 2 to T, IS2 is same as that of the load current na. Even though your load current negative, be careful. Here you can check T by 2 to T, the current is flowing like this na. In this loop, current is clockwise. I0 is negative, but what about the IS2? IS2 is positive only. Yes or no? I0 is like this, IS2 is like this, and current is flowing in this direction. So your I0 is negative, but IS2 is positive. Okay. So yes, this is your Vs by 2R. Vs by 2R. Is this clear? Right? So this is IS2 waveform and IS1 waveform. Next, now can we derive the expression for V0 RMS? Yes, output RMS value of output voltage. V0 RMS value of output voltage. You can check the V0 waveform. We're having 0 to T, whatever the waveform, the same is there, will be repeating from T to 2T, same will be repeating from 2T to 3T. Okay, so it is like 1 by t integration from 0 to t by 2 vs square by 4, and t by 2 to t it is a minus vs by 2 square. Either you can take the RMS value, either you can find over a half cycle or on a full cycle, you will be getting the same value. Okay, so let me write, it is 1 by t integration from 0 to t by 2, it is a vs by 2 na square into dt plus integration from t by 2 to t, it is a minus vs by 2 bracket square into dt to the power 1 by 2, right? If we simplify it, yes, we'll be getting it as a vs by 2 only. This is v0 RMS, right? RMS value of output voltage. What about I0 RMS? I0 RMS, again you can check. I0 RMS is same square wave only. The thing is here magnitude is vs by 2r. Here it was vs by 2. Here it is a vs by 2r. Okay. So I0 RMS, further I can write it as a 1 by t integration from 0 to t by 2 vs by 2r square into dt plus integration from t by 2 to t minus vs by 2r square into dt the power 1 by 2. So it is equal to vs by 2r, which is equal to v0 RMS divided by r, right? This is your I0 RMS. I0 RMS, right? Similarly, can we write IS1 RMS? IS1 RMS, RMS value of switch current. Yes, let me write in general RMS switch current. RMS value of switch current. RMS switch current. Yes, either you can find IS1 RMS or you can find IS2 RMS, doesn't matter. So you can check IS1 waveform, it is like this. Okay, so it is 1 by t integration from 0 to t by 2 vs by 2r bracket square into dt to the power 1 by 2 now. So it is like a vs upon 2r into under root t by 2 divided by t. So this can be written as a vs by 2r into 1 by root t, sorry, 1 by root 2, right? 1 by root 2. Okay, so this is your IS1 RMS. Correct. Next, what is the load power in this case? P0. Load power. Load is purely resistive. So it is a V0 RMS square divided by R, which is equal to I0 RMS square into R, or V0 RMS into I0 RMS, right? So V0 RMS into I0 RMS. Okay. Now you can check here our V0 and I0. These are non-sinusoidal. Okay. Means that it consists of harmonics. Okay. So which harmonics are present? That we are going to discuss. Already in the rectifier chapter, we have, yes, completed the Fourier series analysis of square waveform. Na? Yes or no? Right? So let me write here Fourier series expression. Fourier series expression. Let us write for first V0. Yes, how to write for V0? Yes, whether V0 is a even or odd signal, even or odd function. Yes, it is a odd, right? So odd means what? it is like an is equal to 0. Okay. Next, what about the a0 by 2? That is the average value. Average value is also 0 na. So only thing is we need to find bn. Okay. So now the expression will be, right, it is like summation over n is equal to 1, 2, 3 up to the infinity. It is a bn into sine of n omega t, because an is 0, a0 by 2 is 0. The only thing is bn is there. Okay. Now for already we have done the Fourier series analysis of this type of waveforms na square wave. The only thing is the magnitude is different here. Okay, magnitude is different here, right? So I am directly writing here the expression of, right, Fourier series expression here. Okay, so how it will be? Let me write it as v0 is equal to summation over n is equal to 1, 3, 5, 7 up to the infinity. Because if you find the bn value na, then you will understand for all even values of n, bn is 0. And for odd values of n, bn is non-zero. Okay, so that's why I'm writing directly 1, 3, 5 up to the infinity. Okay, so it is like a 4 into vs divided by n pi. Okay, 4 vs by n pi into sine of n omega t. 4 vs by n pi into sine of n omega t. Right? So sorry, it is a 2 vs, not 4 vs, 2 vs. Okay, 2 vs by n pi into sine of n omega t. How to find it? We know na bn expression. Let me show it in short. bn is equal to what? It is a 2 by t na. Now here we are having, yes, this waveform, right? So it is a 2 by t. Let me write 2 by t integration from 0 to t. It is a v0 into sine of n omega t into d omega t. Further we can write it as, it is like a 2 by t is nothing but, now further what we are going to do, instead of this time I am writing in terms of the angles. So it is like one complete cycle means for sinusoidal or for AC waveform, it is like a 2 pi radian complete na. Okay, so I will be writing it as 2 by 2 pi integration from 0 to pi. T is like your 2 pi. I am converting time to angle. Okay, so it is 2 by 2 pi integration of 0 to pi. It is a vs by 2 into sine of n omega t into d omega t, plus integration from pi to 2 pi. It is like minus vs by 2 into sine of n omega t into d omega t, right? So you can simplify it, right? You will be getting the answer whatever we have written here. For even values of n, you will be getting the 0. For odd values of n, yes, you will be getting it as a 2 vs by n pi. Okay, 2 vs by n pi, right? So this is 2 vs by n pi into sine of n omega t. Now you can check what this expression indicates. This expression indicates v0 consists of only odd harmonics. V0 consists of only odd harmonics. So let me write here. Yes. Yes. Output voltage of half bridge inverter consists of only odd harmonics, because you can check n is equal to 1, n is equal to 3, n is equal to 5, n is equal to 7, 9, etc. These are only present na, 2, 4, 6, 8 are absent. Okay, so only odd harmonics are present. They have asked the question, right, in some of the examinations, the output voltage of half bridge inverter consists of, right? So please keep it in mind, odd harmonics will be present, only odd harmonics will be present. Okay, so now, yes, can I write the output voltage of inverter at n is equal to 1? That is the fundamental frequency. Yes, let me write output voltage of inverter, that is half bridge inverter, at fundamental frequency. Or you can say the output voltage due to fundamental component also doesn't matter. Okay, so this is nothing but your V01. Now in the V0, while writing the expression of V01, I need to put n is equal to 1 simply. It is a 2 vs by pi into sine of omega t. Okay, I am putting n is 1 here. Okay, so it will be like 2 vs divided by pi into sine of omega t. 2 Vs by pi into sine of omega t. Now you can check here. Yes, what this indicates 2 Vs by pi? It is a peak value. It is a sinusoidal, na? So that's why this indicates the peak value. Okay, so let me write it as V01 peak is equal to 2 Vs by pi. So what is the V01? V01 RMS is equal to V01 peak divided by root 2, na? Divided by root 2. So what is V01 peak? 2 Vs by pi divided by root 2. So it is like root 2 Vs by pi. Yes or no? Root 2 into Vs divided by pi. So if you check, it is equal to root 2 by pi. It is 0.45. Okay, so please try to understand this. 0.45 into Vs. This is your V01 RMS. Right? What is our V0 RMS? We have derived V0 RMS. It is a Vs by 2, na? We have written V0 RMS is Vs by 2. Vs by 2 means 0.5 into Vs. Yes or no? So overall output voltage of the inverter is 0.5 into Vs. In that, the fundamental component output voltage is 0.45 into Vs. So please try to understand this. Overall output voltage of the inverter is 0.5 into Vs. In that, the fundamental component output voltage is 0.45 into Vs. So in the 0.5 Vs, 0.45 Vs is of fundamental. So can I say that the share of the fundamental component in the output voltage is 90%? Out of the 0.5 Vs, 0.45 Vs is of fundamental. So share is like 90%, na? So for only remaining 10%, we are having the harmonics. Which are those harmonics? Third harmonic, fifth harmonic, seventh harmonics, ninth harmonic, 11th, 13th, etc. Yes or no? Right? So please try to understand this. V01 RMS is 0.45 into Vs. Okay, 0.45 into Vs. Similarly, can we write output voltage of inverter at third harmonic frequency? Yes, output voltage at third harmonic frequency. At third harmonic frequency. That is V03. Please be careful. Here I am using the word third harmonic. Here it is a fundamental frequency only. Harmonic I have not used, because fundamental is not the harmonic at all. Fundamental is your component. Okay. So yes, V03 is equal to, yes, how to write the expression? Simply here put n is equal to 3. So it is 2 Vs by 3 pi into sine of 3 omega t. Okay. So 2 Vs divided by 3 pi into sine of 3 omega t. Right? So frequency is 3 times of the fundamental. And what is the peak value? V03 peak is equal to 2 Vs by 3 pi. And what is the V03 RMS? 2 Vs by 3 pi divided by root 2, na? So it is like root 2 into Vs divided by 3 pi. So can I write it as 1 by 3 into V01 RMS? Right? Say output voltage, RMS value of output voltage at third harmonic frequency is 1/3 of the fundamental. 1/3 of the fundamental. Actually, fundamental had 0.45 into Vs. So divided by 3 if we do, then we'll be getting V03 RMS. Okay. Means that in the output, the third harmonic share will be lesser than that of your fundamental share. Okay. So similarly, or in general, let me write in general V0n RMS for nth harmonic. It is 1 by n into V01 RMS. 1 by n into V01 RMS, right? So same thing we have discussed. As the order of harmonic increases, its share in the output voltage decreases, na? Right? So the most dominant harmonic is after the fundamental, whatever the next harmonic present, that will be your most dominant. So after the fundamental, whether the second is present, no. So which harmonic is present? Third harmonic. Okay, so the most dominant harmonic is the third harmonic. They have asked the question. Okay, in a single phase half bridge inverter output voltage, right? The most dominant harmonic is a third harmonic. It is a third harmonic. And what is the frequency of that harmonic? It is a 3 times your fundamental frequency, na? 3 omega. You can check frequency of the third harmonic is 3 omega. frequency of the fundamental is, it is a omega only. It is a omega only. Is this clear? Right? So this is what we are having from V0. Now, yes. Okay. So we'll take a break here. It's a 7:15. We'll start at 7:30. Right? We'll start at 7:30. Yes, Ramakrishna, why these gate pulses are large in rectifiers? Okay. In rectifiers, their time was small because you can check here which device, which switches we are using. We are using MOSFET, BJT, IGBT, etc. Na? And whether these switches requires a continuous controlling signal? Yes. So that's why I have represented the controlling signal, that is a continuous for long time. Okay. For SCR, we require a short duration pulse. But in this case, generally SCR is not preferred because of the high switching frequency devices we require. Okay. Yes. So start at 7:30. Yes, Shweta here. Why third harmonic is dominant, not first? Fundamental is not the harmonic. Are you getting the point? Fundamental is the component. Harmonic means your n is equal to 2 and onwards, whatever you are having, those are the harmonics. Okay. So fundamental is not the harmonic, it is a component. So suppose if we are having the pure sinusoidal voltage, the meaning is the share of fundamental is 100%, means the harmonics are absent. Okay. So that's why third harmonic is the most dominant because we are using the word harmonic there. Okay. So if we remove the fundamental, then what will happen? The output voltage will be like, it will be reduced by 90%. Na? So we require a fundamental as 100% actually, right? Okay. Yes, in the purely resistive load, the diodes are not having any functioning. Okay, but for L load, RL load, diodes will be having functioning. Okay, for R load, there is a no functioning of a diode. Yes, we start at 7:30. Yes. So now in the similar way, can we write the Fourier series expression of the I0? You can check the current I0 is also square wave, na? Yes, here it is, we are having I0. It is a square wave. Instead of here Vs by 2, here we are having a Vs by 2R, right? So in the same way, we can write the Fourier series expression of the I0, right? So Fourier series expression for I0, load current I0, right? So it is simply it is I0 is equal to V0 by R. Yes, for V0 we know the Fourier series expression is summation over n is equal to 1357 up to the infinity. It is a 2 into Vs divided by n pi into sine of n omega t. Here we need to add, yes, divided by, here we need to add the r, n pi r, right? That is V0 means this thing divided by r if we do. So it is like 2Vs by n pi r into sine of n omega t. If you check if the load is resistive, whether there exists a phase displacement between voltage and current, no, na, right? If the load is resistive, definitely the voltage and current will be in phase. So here try to understand your fundamental or any fundamental component or any harmonic current will be in phase with that respective harmonic voltage, okay? So let me write here. Similarly, the output current due to fundamental frequency or at fundamental frequency. So output current at fundamental frequency, So can I write it as I01 is equal to 2Vs divided by pi into r na, into sine of omega t. 2Vs by pi r into sine of omega t, right? So from this, what is I01 peak? I01 peak is equal to 2Vs by pi r. So what is I01 RMS? It is root 2 into Vs divided by pi into r. That is peak divided by root 2 now. So it is root 2 Vs by pi into r, right? Similarly, we can write, yes, yeah, we can write output current at third harmonic frequency, output current at third harmonic frequency. So it is I03 is equal to, put here n is equal to 3, 2Vs by 3 pi r, 2Vs divided by 3 pi r into sine of 3 omega t. So I03 peak, again it is 2Vs by 3 pi r, and I03 RMS is equal to root 2 into Vs divided by 3 pi r, right? That is equal to your 1 by 3 into I01 RMS, right? 1 by 3 into I01 RMS. Yes or no? Right? Because you can check the waveform of V0 and waveform of I0. In the waveform of V0, we are having the magnitude is like a Vs by 2, and in a I0 it is a Vs by 2r. So that's why here it is a 2 Vs by n pi r will be getting added here. This r will be getting added, okay? And the phase angle for sinusoidal, for the resistive load, the phase displacement will be 0 now, right? So that's why n omega t here. In the load also, where in the voltage also, where angle, it is n omega t only, right? So in general, I0 n RMS, that is for nth harmonic, is equal to 1 by n into I01 RMS, right? I01 RMS. Now, can we write the output power due to fundamental frequency, that is at fundamental frequency. Yes, let me write output power at fundamental frequency. Fundamental frequency. That is P01. P01. Okay, which is equal to V01 RMS into I01 RMS, right? Because phase displacement is not there, so that's why it will be cos 0. Cos 0 is 1. So that's why it is V01 RMS into I01 RMS. Similarly, output power at third harmonic frequency. Third harmonic frequency. That is N is equal to 3. So it is P03 is equal to V03 RMS into I03 RMS. Similarly, in general, I can write output power at nth harmonic frequency. At nth harmonic frequency. Yes, it is P0N is equal to V0N RMS into I0N RMS. We are having P0 means the total output power of the inverter. That is a P0. P01 is the output power at fundamental frequency. That is due to V01 and I01. P03 is the output power at third harmonic frequency. That is due to V03 and I03. Right? And similarly, we'll be having P05, P07, etc. Okay. So this is about your purely resistive load. Okay. Purely resistive load. Now, suppose for this circuit, yes, same circuit diagram, let us discuss. Yeah. Yes. In this circuit, because some of the times they have asked the question, what is the voltage rating of the switch? What is the voltage rating of the switch required? Yes. Whether it is a Vs by 2, whether it is a Vs, whether it is a 2 Vs. Yes, can anyone? In this circuit, if you check, what is the voltage rating of the switch required? You can check when S2 is in an on state, S1 is in an off state. Na? So what is the voltage that will be appearing across the S1? Voltage appearing across S1 is nothing but voltage between these 2 points. Okay. So again, this point is connected here. This point through S2, it will be connected here. So can I say that the voltage across S1 is nothing but voltage, this full voltage, that is Vs by 2 plus Vs by 2. That is a Vs, na? Yes or no? Right? So voltage rating of the switch, it is a Vs. Voltage rating of the switch is Vs. It is not Vs by 2. Please be careful. It is a Vs. Is this clear? It is a Vs. Right? So next. Now let us discuss with the L load. Okay, L load, purely inductive load. So let me put the heading. Single phase half bridge inverter. HBI means half bridge inverter with a pure L load, purely inductive load. Okay, so the same circuit diagram, let me draw. Now in the load, we are having an inductor. And we know inductor is the element which stores energy and it releases the energy. Right? This is Vs by 2. Inductor L, this voltage is V0. Current is I0, S1, S2, D1, D2, IS1, IS2, ID2, ID1, right? So the waveforms. V0, I0, IS1 T by 2 T, and it is like a 3T by 2 T by 2 T and 3T by 2, right? So output voltage will be getting, it is a square wave only. This is magnitude is Vs by 2. I0 is a linear, it is a ramp type signal. Okay. Why it is a linear and ramp type, we'll discuss. T by 2, this is a T. This point is like T by 4. This is like 3T by 4. Okay. 5T by 4. So on. Let me draw the IS1 waveform. We can draw the other waveforms also, that is IS2, ID1, ID2 also, right? Suppose the peak value is like a plus I0 and here it is like a minus I0. Okay. Now, which devices will be in a conduction mode? Let me indicate. Yes. So it is like yes, one conducts, inductor stores energy. After that, D2 conducts, S2 conducts, D1 conducts. Here it is D1, so it is a D1. Okay. So single phase half bridge inverter with purely inductive load. So here I have not drawn the waveform of IG1, IG2. Okay, but IG1 and IG2 waveforms will be same as that of the previous case. That is omega t, that is t is equal to 0 to t by 2. Get pulse is applied to switch S1. T by 2 to capital T. Get pulse is applied to the switch S2 actually. Okay, so 0 to t by 2 IG1 is there. T by 2 to t IG2 will be there. Okay, so same. Now let us discuss the circuit operation. For very first cycle, I am saying for very first cycle. Okay. That is at t is equal to 0. For very first cycle at t is equal to 0, switch S1 will be turned on. I am saying for very first cycle. This is like for continuous cycle. This is negative. It is starting from negative, means it is a continuous cycle. But for very first cycle, I am saying, so for very first cycle from 0 to t by 2, it is like switch S1 is in a conduction mode. So when S1 is in a conduction mode, current is flowing like this. Very first cycle means before that cycle, the circuit was at the rest position. So therefore current flowing through the inductor will be 0, right? So it is like inductor has not stored any energy. So at t is equal to 0, as soon as we apply the gate signal or we apply the controlling signal to the switch S1, our switch S1 will turn on. So when S1 turns on, current starts flowing in this loop. Okay, current will be flowing Vs by 2, S1 load, and again back to the Vs by 2. Okay, so here V0 will be like your Vs by 2 only. Okay, 0 to t by 2, V0 is Vs by 2. What about the I0? Here we are having inductor. Before this cycle, right, inductor current was 0. So therefore inductor will oppose the change in the current. Okay, so therefore yes, inductor current will go on increasing slowly. It is linear only, but it is increasing slowly. Okay, so straight line. Next, this is for very first cycle only, but for continuous cycle it will start from negative. Why it is starting from negative, we'll discuss. Okay, so now let us suppose at t is equal to t by 2, at t is equal to t by 2, I have turned off the S1. I have turned off the S1. What will happen? And I have turned off the S1 and I have applied the gate pulse to S2. I have turned off the S1 and I have applied the gate pulse to S2. So what will happen? Whether this inductor will allow the turning on of a S2? No. Why? Because you can check when S1 was in a conduction mode, current flowing through the inductor was in this direction, that is from right to left. Corresponding to T/2, current flowing through the inductor is plus I0, that is a non-zero current. Yes or no? When S2 turns on, right? Because for S2 to be turned on, to be in the on state, okay? Yes, what will happen? This inductor will oppose. How? Because this inductor will try to maintain the current in the same direction, right? So even though we apply the gate signal to switch S2, that is the controlling signal to S2, but immediately at T/2 our S2 will not turn on at all. Why? Because of this inductor. So now what will happen in the circuit at from T/2 to 3T/4, from T/2 to 3T/4. Okay. Actually, the thing is this inductor will go on releasing the energy through diode D2. Inductor will go on releasing the energy through diode D2. Okay. Means it is like inductor is releasing the energy. Inductor is releasing the energy through diode D2. Means after S1, which switch should be in a on state? That is the diode D2 should be in a conduction mode. Okay. So diode D2, inductor releases energy. Inductor releases energy. This will, you can check when inductor releases energy, we know now slope is negative. Slope is negative. So that's why here current is decreasing. Current is decreasing. This will, now you can check when inductor releases energy through diode D2, means diode D2 in a conduction mode. So what is the V0? You can apply KVL. Minus V0 minus Vs/2. Minus V0 minus Vs/2 is equal to 0. So minus V0 minus Vs/2 is equal to 0 means V0 is minus Vs/2, right? So here we are having the output voltage is negative. Till this instant, output voltage is negative, that is minus Vs/2. And what about the current? Current is decreasing because inductor is releasing the energy in this loop. In this loop, the inductor is releasing the energy. So when inductor releases energy, what about the current in the load branch? In the load branch, current is flowing from right to left only. So right to left current is flowing means current I0 is positive or negative? Current I0 is positive only. Okay. So current I0 is positive, but it is decreasing because inductor releases energy. This will continue till 3T/4. At 3T/4, what will happen? At 3T/4, we have already applied the controlling signal to S2, but at that instant, whether S2 has turned on at T/2? No. Now S2 will turn on at 3T/4. 3T/4, S2 will turn on. So at 3T/4, what will happen? It is like inductor has released the energy now. Okay. So diode will be in an off state, right? And due to that, our S2 will turn on. Once S2 turns on, current will be flowing like this. Current will flow in this loop. Are you getting the point? So current is flowing like Vs/2, inductor load, inductor S2 and again back to the Vs/2. Current is flowing Vs/2, inductor S2 and again back to the Vs/2. In this loop, the current is flowing. So if the current is flowing into this loop, what about the V0 and I0? You can apply KVL. Current is flowing in this loop. I am saying current direction is here. It is, you can check in this branch. I am saying current in this loop is clockwise, means in this branch current is left to right. Okay. So apply KVL. You will be getting plus Vs/2 plus V0 is equal to 0. Plus Vs/2 plus V0 is equal to 0 means V0 is equal to your minus Vs/2 now, right? So V0 is negative only. Till T, V0 is negative. Minus Vs/2. What about the I0? Here as S2 is in the on state, inductor has already released the energy till 3T/4. So after 3T/4, what will happen? Inductor again go on storing the energy now. So here when S2 conducts, inductor stores energy. But what is the direction of the load current here? You can check direction of the load current is from left to right, means I0 is in negative. So I0 is increasing, but it is in negative. It is increasing in the negative direction, right? So this will continue till T. At T is equal to capital T, we are turning off the switch S2. We are turning off the switch S2. Okay. So at T is equal to capital T, yes, we have turned off the switch S2, and suppose if we apply the gate pulse, right, to the or the controlling signal to the switch S1, but whether our inductor will allow the turning on of a switch S1? No. Why? Because corresponding to capital T, inductor current is, it is a non-zero current, right? And direction of the current is like this. So whether our inductor will oppose the turning on of a switch S1? There, yes, definitely. So therefore, what will happen? Our inductor will release the energy through diode D1. Inductor will release the energy through diode D1. Okay. So here you can check when inductor releases energy through diode D1 here, current in this loop, it is in an anti-clockwise direction. Current in this loop is in a anti-clockwise direction. Okay. So after S2, which device is in a conduction mode? D1. After S2, D1 is in a conduction mode. Inductor releases energy. Inductor releases energy. So here inductor is releasing the energy, or you can say it is like inductor is feeding power back to the supply, na? Because inductor is releasing energy through Vs by 2. Means what? Inductor is feeding back power to the Vs by 2. That is a source. So that's why in inverter, these diodes are known as a feedback. These diodes are known as feedback diodes. These are not the freewheeling diodes. These are the feedback diodes. Okay, feedback. Why it is feedback diode? Because load is feeding back power to the source through these diodes. Through these diodes. Okay. So now you can check here. Inductor is releasing the energy through diode D1. Okay, and S1 is in off state, so you can apply KVL to this loop. You can apply KVL to this loop. It is like minus Vs by 2 plus V0 is equal to 0. Minus Vs by 2 plus V0 is equal to 0 means what? V0 is equal to your Vs by 2. So after T, you can check here V0 is equal to positive now. V0 positive, current is decreasing. Current is definitely negative only because inductor releases energy like this now. So current is negative, but it is decreasing. Means what? Here the inductor is releasing the energy. Inductor is releasing energy, right? So at 5T by 4, at T is equal to 5T by 4, it is like inductor energy becomes 0. And our next switch S1 will turn on. So at 5T by 4, when S1 turns on, what will happen? Again, the current will flow like this, Vs by 2, S1 load, and again back to the Vs by 2. So what is the direction of load current? You can check the direction of load current is from right to left now. Means I0 is positive or negative? I0 is positive. Okay. So current is flowing like this. Again, inductor stores energy. Okay. So after 5T by 4, it will be like this waveform will be getting. You can check V0, apply KVL, you will be getting V0 is equal to Vs by 2. So during this interval, V0 is Vs by 2. So for very first cycle, it was like this, starting from 0. But for continuous cycle, you can check after T, na, 0 to T, whatever the waveform we are having, the same is repeating. Na? So after T, you can check in the I0, we are having a negative pulse. Na? So same negative pulse in the continuous cycle will repeat at T is equal to 0. Na? Yes or no? So that's why if this is minus I0, definitely this is minus I0. If this is decreasing, definitely this will be decreasing. Are you getting the point? Okay. So please try to understand the conduction of the switches. It is like through S1, S2, inductor stores energy. Through D1, D2, inductor releases energy, but it is in opposition to that of the supply voltage. The meaning is inductor or the load is feeding power back to the supply. Okay. Load is feeding power back to the supply. Okay. So now, so conduction of the switches, you can check S1, D2, S2, D1, and again S1, D2, S2, D1. It repeats, it go on repeating. Okay. So now let us understand. Okay. Or let me first write here. Yes. Interval conducting device. And V0, right? Yes. And let me write I0 also. So during interval T by 4 to T by 2, T by 4 to T by 2. I'm starting with T by 4, right? During T by 4 to T by 2, which switch is in on state? It is a S1. It is like inductor stores energy, right? When S1 is in on state, inductor go on storing the energy. So I0 positive and it is increasing. V0 is Vs by 2. So V0 is a Vs by 2 and I0 is a positive. It is increasing. Inductor stores energy. During the second interval, that is T by 2 to T. Sorry, T by 2 to, yes. You can check it is a 3T by 4. T by 2 to 3T by 4. Which device is in on state? So T by 2 to 3T by 4 means inductor releases energy through diode D2. Okay. So diode D2 is in a conduction mode. So when D2 is in a conduction mode, how is the output voltage? You can check output voltage is a negative. Okay. Output voltage is a negative. That is minus Vs by 2. And what about the I0? I0 is positive, but it is decreasing. Okay. So I0 is a positive. Next, from 3T by 4 to T. From 3T by 4 to T. Switch S2 conduction mode. Okay, S2 conducts. So inductor again go on storing the energy, but I0 is negative. So inductor stores energy, I0 is negative. Okay, so let me write here. Inductor stores energy and I0 negative, S2 conduction. Okay. What is the output voltage? It is a minus Vs by 2 and I0 is negative. And similarly from T to, it is like a 5T by 4, no? From T to 5T by 4. S2 off state. So what will happen? Inductor releases energy through diode D1. Okay. So after S2, D1 conducts. So it is a D1. D1 conducts, so output voltage is Vs by 2. And what about the I0? I0 is negative. Okay, I0 is a negative, right? So this is the conduction of the devices, right? Okay, so next, so here can we say that each device conducts for T by 4 time only? Yes or no? Each device conducts for T by 4 time only. You can check here, 0 to T by 4 D1 conducts, T by 4 to T by 2 S1 conducts, again for next T by 4 D2 conducts, right? So let me write here, each device for purely inductive load, I am saying each device, or you can just say switch, okay? Each device conducts for T by 4 time, okay? T by 4 time, okay? This is important. Next, now let us discuss why it is a linear I have drawn. Why it is linear I have drawn. Okay, let us discuss. Now you can check during 0 to T by 2. During 0 to T by 2, what is V0? It is a Vs by 2 now, right? So let me write here. During T is equal to 0 to T by 2. T is equal to 0 to T by 2. Yes, we are having V0 is equal to Vs by 2. Now in the load, we are having only inductor. So can I write this I0? Can I write the V0 is nothing but voltage across inductor only? What is the voltage across inductor? It is L into di0 by dt. Na? So can I replace this V0 with L di0 by dt? So it is a L into di0 by dt is equal to what? It is a Vs by 2. Yes or no? Right? So can I write therefore di0 by dt is equal to Vs by 2L. Right? This is what the slope of your I0 waveform. Slope of the I0 waveform. Let me write. This is slope of I0. Slope of I0. It is a Vs by 2L. Now further I can write it as di0 is equal to Vs by 2L into dt. So if we integrate both these sides, it is like integration of di0 is equal to integration of Vs by 2L into dt. So can I write it as I0 is equal to Vs by 2L, right? Vs by 2L is a constant or variable? Vs is the supply voltage. It is a constant. 2 is a constant. And L, that is the inductor, na? It is a load inductor. It is also constant. So Vs by 2L is a constant. So integration of dt is a t. So please try to understand. This I0 is equal to Vs by 2L into t. The meaning is this is like I0 is a constant into t, na? So it is like your ramp signal, na? Y is equal to mx type thing. Okay, so it is like a linear. So that's why here as I0 is proportional to time. So that's why it is a linear. That's why it is a linear. Are you getting the point, right? So you can check here in this waveform, it is a linear we are getting a linear. Okay. So now what is the slope? Slope is Vs by 2L, right? Vs by 2L. Now here, yes, you can check. I have shown it as a changing from minus I0 to the plus I0, and again from plus I0 to the minus I0, minus I0 to the plus I0. Okay. So can we write the peak value? Yes, with the help of this di0 by dt, can we write the peak value, that is the I0? Yes, we can write. You can check here as the slope is di0 by dt, which is equal to Vs by 2L, na? Vs by 2L. So let me write it as at t is equal to 0, I0 is equal to minus I0. Okay, small I0 is equal to minus I0, na? Small I0 is equal to minus I0, right? So if we want to find the I0 value, what we are supposed to do, you can check here. di0 by dt is equal to, yes, you can check this waveform. di0 by dt, that is the change in the current with respect to time. So how the current is changing? Current is changing from minus I0 to the plus I0. So final value is plus I0. Initial value is minus I0. So can I write it as plus I0 minus of minus I0, right? That is nothing but your di0 now. So let me write it as plus I0 minus of minus I0 divided by how the time is changing. The time is changing from 0 to t by 2. So it is t by 2 minus 0. Okay, so time is changing from 0 to t by 2. So it is t by 2 minus 0. Are you getting the point? di0 by dt means change in the current. That is, current is changing from minus I0 to the plus I0. So it is plus I0 minus of minus I0 and divided by dt is nothing but t by 2 minus 0. Okay, so let me write it as di0 by dt is equal to, this is like a 2I0 divided by, yes, t by 2. Or let me write it as a 4I0 divided by t. Okay, 4 into I0 divided by t. Next, what is di0 by dt? We have written it is Vs by 2L. Na? So can I write it as Vs by 2L here? So it is Vs by 2L is equal to 4 into I0 divided by t. So further from this I0, so therefore I0 is equal to, we can write it as, yes, Vs into t. Okay, Vs into t divided by 8L. Okay, Vs into t divided by 8L. This is nothing but your I0. Means your current is changing from minus Vs t divided by 8L to the plus Vs into t divided by 8L. Okay, plus Vs into t by 8L. Okay, so what is the peak value of the I0? Peak value of I0 is plus I0, that is the Vs into t by 8L. Yes or no? Right? So let me write peak value. Peak value of I0 is equal to, this should be the small I0, which is equal to capital I0 is equal to Vs into t divided by 8 into L. Vs into t by 8 into L. Right? Next. So what is the peak to peak difference? Come on, peak to peak difference means plus I0 to the minus I0. The difference is plus I0 minus of minus I0. That is a 2I0 now, right? So let me write peak to peak difference. Peak to peak, or you can say peak to peak ripple also. Okay, peak to peak ripple in load current I0. Okay, in load current I0 is equal to I0 minus of minus I0. That is final value minus initial value. Okay, so it is equal to 2 into I0. So if I multiply with 2, okay, so I0 is this thing we are having. So if I multiply with 2, you will be getting it as Vs into t divided by 4 into L. Right? This is your peak to peak ripple in the load current. That is Vs into t by 4 into L. Is this clear? Right? So this is your peak to peak ripple. This is your peak value of the load current. And yes, this is the peak value of the load current, right? Means load current changes between minus I0 to the plus I0. So on which values your I0 magnitude depends? It depends on your supply voltage value, your inductor value, and your, yes, switching frequency. That is the time t. Okay, time t. It depends, right? Okay. Is this clear? So please try to understand. Purely inductive load, each device conducts for t by 4 time only, right? Yes, means exactly it is passing through the center of 0 to t by 2, the center means center of these 2 points, that is t by 4. Similarly, the center of these 2 points, similarly center of these 2 points. Okay, it is crossing the zero crossing it is having, right? Yes. Next, so this is IS1 waveform we draw. Similarly, can we draw the waveform of IS2, ID1, ID2? Yes or no? Yes, let me draw the waveforms of, yes. First, let us draw the waveform of IS2, t by 4, t by 2, 3t by 4, and here it is a t, right? IS2, ID1, and ID2. Yes. How is the waveform of IS2? You can check the switch S2 is in a conduction mode from 3t by 4 to t, 3t by 4 to t. Okay. But when S2 conducts, how the current flows? current will be flowing like this na. Load current is negative, but IS2 is positive only. Please be careful. Load current is negative, but IS2 is positive because current in this branch is, it is a clockwise direction. So IS2 positive, I0 is negative, right? So here the thing is, current is increasing in the negative direction means inductor is storing the energy. Okay, so IS2 waveform, that is from 3T/4 to T. It will be like this, 3T/4 to T. This is the IS2 waveform, right? Next, how about the ID1 waveform? You can check the ID1 waveform. Here it is D1 conduction mode. Here it is also D1 is a conduction mode. Okay. So from 0 to T/4, D1 is in a conduction mode. So when D1 conducts, what happens in the circuit? Suppose D1 is in a conduction mode. It is like inductor releases energy, na? So your I0 is negative, but what about the ID1? ID1 is positive. Yes or no? I0 is negative, but ID1 is positive. So I0 is like this, that is, it is starting from non-zero negative value and it is moving, approaching the zero value. Okay, non-zero to the zero, it is approaching the zero value. Okay, so if I want to draw the ID1 waveform, it will be like this, ID1. Like this one is, and after that, here it is also, it repeats. Okay, so you can check corresponding to T is equal to 0, it is a positive non-zero. And in the I0, if you check the waveform at T is equal to 0, I0 was a negative non-zero value. Okay, so that's why it is negative. So opposite to that of this is nothing but positive will be there. That is for ID1, right? What about the ID2? ID2 conducts from T/2 to 3T/4. Okay, so when ID2 conducts, it is like inductor go on releasing the energy like this, right? So ID2 positive, I0 negative. So ID2, yes, like this. Sorry, I0 and ID2 both are positive. This type. In the anti-clockwise direction, current will be flowing. So I0 positive and ID2 is also positive. Okay, so the waveform will be like this. ID2. So this type of waveform, right? So IS2, ID1, ID2, and IS1 we have already drawn, right? Yes. So next, can we write the Fourier series expression of V0 and I0 here? Yes, please check Fourier series expression. Fourier series expression. Okay, so let us first write for V0. If you compare this V0 waveform and whatever the V0 waveform we discussed in the previous case, that is for R load, whether both are same or different. Come on, whether the V0 waveform here and V0 waveform in the previous case, whether both are same or different. Both are same. Sir, ID2 waveform is in wrong interval. Okay. Let me check. Yes, ID2. This should be in third interval. Okay, correct. Thank you. ID2 should be in third interval, right? Yes. Right. Okay. So, yes, V0 waveform with purely inductive load and V0 waveform with R load, both are same, right? So whatever the waveform, whatever the Fourier series expression we wrote there in a R load, the same expression we can use here, right? So let me write V0 is equal to summation over N is equal to 1357 up to the infinity. Okay, it is a 2 Vs divided by N pi into sine of N omega t, right? This is your V0. How to write the I0 expression? Please try to understand. This is important. I0 expression. Now we are having a purely inductive load. Okay, so in general, I am writing in general. So if we are having a combination or if we are having a pure, right, we will discuss what to do. So N is equal to 1357 up to the infinity. It is same 2 Vs by N pi. That is your V0 as it is. Into, we need to write Zn. Okay, we need to write a Zn here. What is Zn? We'll discuss. Okay, into sine of n omega t minus phi n. You can write phi n or you can write theta n also, doesn't matter. Okay, so please try to understand this, where Zn is nothing but impedance offered by the AC circuit to the nth harmonic current, okay, which is equal to under root r square plus n omega L bracket square. This is a Zn, and phi n is equal to tan inverse of n omega L divided by r, n omega L by r. Okay, so let me write here Zn. It is impedance offered by circuit, right, to nth harmonic current. Okay, so please try to understand this. What we have done for the purely resistive load, directly I wrote this Zn is nothing but R. Yes or no? Because you can check in a purely resistive load, this Zn is like under root r square plus whether the inductor was present there. No, so that's why this term will be like a 0. So it is like under root r square only, na? Under root r square means r only. So that's why Zn is equal to r only. In the purely resistive, I am saying. Also in the purely resistive load, if you check, what about the phi n? Phi n is equal to tan inverse of n into omega L by r. But whether in a purely resistive load, inductor was present? No. So that's why this n omega L term will be 0. So it is like tan inverse of 0 by r. Tan inverse of 0 by r means tan inverse of 0 only. What is tan inverse of 0? It is a 0 only. So that's why phi n was 0, right? Means the same expression you can use there also, but you yes, you will be getting Zn is equal to r, phi n is equal to 0. Now in this case, okay, now in this case, this is a generalized expression I have written. See, generally for combination of the impedance, means two elements, resistor, inductor, okay, that's that type of thing. But in this circuit, suppose if I want to if I want to modify this I0 expression, here Zn is equal to under root. Now whether the resistance is present in a purely inductive case? No. So R is equal to 0. So it is like only under root n omega L bracket square. Yes or no? So Zn is equal to this term only, that is n omega L only. And what about the phi n? Phi n is equal to tan inverse of this term. Resistance is not there, na? So it is like tan inverse of n omega L. This is a non-zero term divided by resistor. Resistor is not present, so that's why it is a divided by 0. So tan inverse of finite term divided by 0 means it is a tan inverse of infinite. What is the tan inverse of infinite? It is a 90 degree, na? So that's why phi n is equal to 90 degree. Are you getting the point? This is for purely inductive load I am saying. For purely inductive load I am saying. Okay, so for L load I am modifying it. For pure inductive load. For pure inductive load, what is Zn? Zn is equal to under root 0 square plus n omega L bracket square, which is equal to n omega L only. Okay, this is your Zn. And what about the phi n? Phi n is equal to tan inverse of n omega L divided by 0, which is equal to pi by 2. That is a 90 degree. So therefore I0, let me write, therefore I0 is equal to same expression 2 Vs by n pi, or summation over n is equal to 1357 up to the infinity 2 Vs divided by n pi into, I am writing Zn. Zn is nothing but this term only, okay, into sine of n omega t minus pi by 2. Sine of n omega t minus pi by 2, right? Is this clear? Okay, so this is your I0. This is the I0. Right? This is for pure inductive load. Pure inductive load. You can check in simple AC circuit also, na, if the load is purely inductive, what is the phase difference between current and voltage? It is a 90 degree, na? Current lags the voltage by 90 degree. The same here we are getting. Okay, it is a pi by 2. We are getting pi by 2. Now, please try to understand what this Zn meaning. Because you can check in the circuit whether we are having only fundamental component. No, we are having a harmonics also, third harmonic, fifth harmonic, seventh harmonic, 9th, 11th, 13th, etc. Okay, so this Zn is nothing but, and whether for each current we are having the same frequency? No, na? Frequency of a fundamental is omega. Frequency of a third harmonic is 3 omega. Fifth harmonic it is a 5 omega. Seventh harmonic it is a 7 omega, etc. Okay. So as the frequency of the each harmonic current is different, so therefore whether the impedance offered by that respective circuit will be same or different, definitely it should be different now, because in the impedance we are having a resistive part that is independent of frequency, and another part we are having it is the inductive part now, and inductive part depends on reactance offered by the inductor, it depends on the frequency, right? So that's why frequency is different. So that's why here we need to consider it is n omega L. It is not omega L, it is a n into omega L, because we are discussing for nth impedance, that is nth harmonic impedance. Are you getting the point? Yes or no? Okay. We'll discuss the doubts at the end of the session. Okay. Right. Correct. Okay. Okay. So this is your I0 expression. Okay. Now you can check here for all the harmonics. For all the harmonics, here where angle is 90 degree. Na? For voltage, what is the angle? For voltage, the angle is, it is like n omega t plus 0. Here it is n omega t minus pi by 2. So can I say that in a purely inductive load, each harmonic current is lagging to its respective harmonic voltage by angle 90 degree? Yes or no? Means angle between V01 and I01 90 degree. V03 I03 angle is 90 degree. V05 I05 angle is 90 degree. So what is the output power here? Can anyone, what should be the output power here? It is Vi cos phi. Angle is 90 degrees, so it is cos 90, 0 na, right? So output power in a purely inductive load is 0 only. Is this clear? Right? So it is a 0 only. Yes, Ramakrishna, actually, yes. In order to find, okay, in order to find this I0 Fourier series expression, simply we are using V0 by impedance thing. Are you getting the point, right? We are not finding the Fourier series expression of this waveform, right? We are not finding the Fourier series expression of this waveform. Are you getting the point? Okay, right. Yes. Or simply you can check this angle is minus pi by 2 na. The meaning is it is like we have shifted, yes, let me show here. Yes, it is like we have shifted this waveform first of all to this side. Okay, means by pi by 2 radian. This is 0, this is t by 2, this is t. 0 to t is 360 degree na. So 0 to t by 2 is like a 180 degree. So 0 to t by 4 is 90 degree. If I shift this waveform by 90 degree to the left hand side, so this point will be coming here, right? So whether I will be getting the even or odd signal, I will be getting the odd signal. Yes or no, right? So an will be 0 here. Okay, so and after finding that I0 dash Fourier series, again we can find, yes, by putting the angle minus pi by 2. So that's why here the angle is minus pi by 2, right? So in both the ways you can check, but the simple way is V0 by impedance. V0 by impedance. Yes, yes. Correct. Okay. So output power is a 0 only. Output power is a 0 only, right? Next, so this is about your purely inductive load. Okay, purely inductive load. Next, let us discuss for RL load what will happen. For RL load, single phase half bridge inverter with RL load. RL load. Yes. let me put the RL load. Let us draw the circuit diagram. S1, S2, D1, D2, right? So yes, for RL load. V0 time to 0. It is a RL load, so it will be having the combination of, okay, resistive and inductive part. So your current expression or the current waveform will be like a exponentially rise and exponentially fall. Okay, so this type of current waveform will be getting exponential rise and exponential fall type. It is not linear, it is an exponential rise, exponential fall. Okay, so it is like a minus I0. Suppose this is a plus I0. So which devices will be in a conduction mode? Let me indicate. It is a S1 here. After that, inductor releases the energy, so D2. After that, inductor stores energy, so S2, and again after S2, D1. Okay, so yes. So let us discuss the circuit operation. In the L load, it is a linear and it is exactly passing through the center point. But here, yes, sir. Can you please move the node for letting current at odd harmonic? Yes. Yeah, I will upload it by tonight only. Sir, why not we take power as VRMS into IRMS? Which power you are saying? Overall power? Output side is AC or DC? It is a AC. In the AC, what is the power? Yes, VI cos phi, na? Right? So VI cos phi means we need to consider the angle also, right? So, right. So, yes, now let us discuss the circuit operation. It is like 0 to T by 2 and T by 2 to T, right? 0 to T by 2, T by 2 to T. Now, definitely, we are going to apply the controlling signals to the S1 from 0 to T by 2 and to the S2 from T by 2 to capital T. Okay, so now let us discuss the circuit operation. So let us start with, yes, definitely for very first cycle, it will start from 0. But for continuous cycle, it will be starting from negative, just like whatever we are having here, na? That after T means what? Whatever the same pulse here, the same will be repeating here. Okay, so let us check with this instant. Let me indicate this instant as T1. Indicate this as a T1. This is T1. This is T by 2 we are having. Let us consider this as a T2. And here it is like a T, right? This is a T we're having. Now let us check for T is equal to T1 to T by 2. For T is equal to T1 to T by 2. For T is equal to T1, small t1 to T by 2. T1 to T by 2. It is like S1 is turned on. I am considering directly this interval. Okay. So S1 is turned on because during 0 to T1, what will happen? That you will understand when I discuss the T2. This is like, let us consider it as a T3. Okay. So T1 to T by 2, S1 is turned on. So S1 is in on state. So when S1 is in on state, it is like, yes, switch S1 is turned on. Current will be flowing from Vs by 2 S1 load and again back to the Vs by 2. Yes or no? Current will be flowing from Vs by 2 S1 load and again back to the Vs by 2. But here we are having the inductor and a resistor in the circuit. Whether our inductor will allow the sudden change in the current? No. So that's why the I0 will be changing like this. I0 will be changing like this. Okay. So it is like inductor go on storing the energy. Let me show here, right here. Inductor L stores energy. Stores energy. So what about the I0? Whether it will be increasing or decreasing? When inductor stores energy, di0 by dt is positive, right? So definitely I0 will be increasing. Okay. So I0 will be increasing. Yes. Can we apply KVL to this loop? You can check S1 is in on state. We can apply KVL. It is plus Vs by 2 minus V0 is equal to 0. So what is V0? V0 is equal to Vs by 2. So let me write it as V0 is equal to Vs by 2. And what about the I0? It is increasing. So you can check from T1 to T by 2. From T1 to T by 2. Yes, I0 is increasing and V0, T1 means somewhat here. Okay. V0 is Vs by 2 only. This value is Vs by 2. Right? Vs by 2. Now, so this is Vs by 2 and this is increasing. Inductor has stored the energy now. At T is equal to T by 2, we are going to turn off the switch S1. We are going to turn off the switch S1. So when S1 is turned off and if we apply the controlling signal to the S2, then what will happen? Yes, before that is T1 to T by 2 current flowing through the inductor. It was in this direction. So when S2 is turned on, current flowing through the inductor in the load branch, you can check S1 is in a conduction mode, means current is in this direction, that is from right to left. But whether our inductor will allow the switch S2 to turn on immediately? No. So what will happen? This inductor will release the energy through diode D2. So after S1 again diode D2 will conduct. So current will be like this. Current will be like this. This is again exponentially decreasing only. Exponentially decreasing. Okay. So let me write from T by 2 to T2. For T is equal to T by 2 to T2. What is happening? Diode D2 conducts. Diode D2 conducts. Inductor releases energy, na? Releases energy. And what about the I0? I0 decreases. I0 decreases. So what about the V0 here? You can check when D2 conducts the V0. You can check anti-clockwise direction current is flowing. Minus V0 minus Vs by 2 is 0. Minus V0 minus Vs by 2 0 means what? V0 is minus Vs by 2, no? Right? V0 is equal to minus Vs by 2. Right? So V0 is a negative now. So here you can check T by 2 to this instant. V0 is a negative. At T by 2, actually we applied the controlling signal to S2 during T by 2 to T, but actually S2 will turn on at T2. S2 will turn on at T2, right? Because before that it is like inductor was opposing, right, to turning on of a switch S2. Okay, so that's why at T2 till T, from T to T, capital T. Okay, switch S2 is in a conduction mode. So when S2 is in a conduction mode, what will happen? Current will be flowing like this, na? Okay, so let me write for T is equal to T2 to capital T. Capital T. S2 is in a on state. S2 is in a on state. So when S2 is in a on state, current is flowing like in a clockwise direction. Again, inductor go on storing the energy. Current is in a clockwise means I0 is negative, na? And it is increasing. So it is negative increasing. Okay. Inductor stores energy, right? So inductor L stores energy. what is the V0? You can apply KVL plus Vs by 2 plus V0 is equal to 0. So V0 is minus Vs by 2. Right? So this is during T2 to capital T. Next, for T is equal to T to T3, we have written, no? Right? T to T3, you get either you can write T to T3 or you can write T to T plus small t1, doesn't matter, right? Because if you check, if this interval is T1, 0 to T1, then this should be also 0 to T1 only, right? So T3 is like your capital T plus small t1, capital T plus small t1, right? So that's why. So here you can check during this interval what will happen. Now, when S2 conducts, it is like inductor stores energy. Na? When S2 turns off, inductor releases energy through diode D1. Okay, means after this D1 conducts, and the same waveform here, the same will appear here. Okay, so let me write here T2 T3, or let me write it as, or it is T is equal to 0 to T1. Okay, both are same, huh? Both are same, right? So it is like a diode D1 is in a conduction mode. Inductor releases energy. Releases energy. You can check V0. V0 is equal to Vs by 2. V0 is equal to Vs by 2, right? So we're having V0 is a positive, right? And current is decreasing. Inductor releases energy, right? So this type of waveform will be getting for RL load. So let me write for RL load. For RL load. For RL load. I0 is exponential rise and exponential fall, right? Okay, so now can we write the expression of that I0, why it is exponential rise and exponential fall? Let us discuss. Okay, so you can check. Yes, during 0 to T by 2, V0 is Vs by 2 na, right? So can I write during 0 to T by 2, during T is equal to 0 to T by 2, V0 is equal to Vs by 2. Again, what is V0? In the load branch, you are having R and L na. So V0 means what? You can check here. V0 means potential difference between this point and this point. Across between these 2 points, we are having a resistor and inductor, right? So can I write V0 is equal to R into I0 plus L into di0 by dt? Yes or no, right? So it is a R into I0 plus L into di0 by dt, which is equal to Vs by 2, right? So further I can write therefore di0 by dt plus R by L into I0 is equal to Vs by 2 into L na. I have divided with L in order to make the coefficient of this di0 by dt to be 1. Okay, so whether this is a differential equation? Yes. So how to find the solution of this differential equation? Yes. Yes. Solution, we need to find the integrating factor. Okay, so let me write integrating factor is equal to e to the power integration of R by L into T na. So it is equal to e to the power RT by L, e to the power RT by L. So solution is I0 into e to the power RT by L, that is Y into IF, is equal to integration of Q, that is Vs by 2L into e to the power RT by L into dt plus C, Y into IF, dy by dx plus Py is equal to Q. You might be knowing. Okay, so Y into IF is equal to integration of Q into IF dx plus C. Instead of x, now we are having T. So that's why I written dt. So how to simplify? I0 into e to the power RT by L is equal to Vs by 2L into e to the power RT by L divided by R by L. Okay, divided by R by L plus C na. So you can check L will get cancelled. So it is like I0, therefore I0 into e to the power RT by L is equal to Vs by 2R, Vs by 2R into e to the power RT by L. e to the power RT by L plus C na. Consider as equation number 1. We need to find the value of this C also. At t is equal to 0. How to find? At t is equal to 0. What is your I0? It is a minus I0 now. You can check steady state operation. At t is equal to 0, I0 is a negative minus I0. Right? So let me write here. At t is equal to 0, I0 is minus I0. So from 1, can I write? Can I replace this I0 with minus I0 and t with a 0? Yes. So it is a minus I0 into e to the power 0 is equal to Vs by 2R into e to the power 0 plus C. So therefore I can write C is equal to minus I0 minus Vs by 2R. This is your C. We need to put this C in equation 1, right? So put this is C in equation 1. So we can write it as I0 e to the power RT by L is equal to Vs by 2R into e to the power RT by L, right? Minus I0 minus Vs by R, minus I0 minus Vs by 2R. Yes or no? So further what we can do, this is Vs by 2R, this is Vs by 2R. So I can take it outside. Okay, so therefore it is equal to Vs by 2R into, it is like a e to the power. Yes, before that, yes, let me write. Yeah. Let me write I0 first, and after that we will take a common. So next, can I shift this e to the power RT by L to the right hand side? Yes, so it is a I0 into Vs by 2R minus I0 into e to the power minus RT by L minus Vs by 2R into e to the power minus RT by L. So or no, I have shifted this e to the power RT by L to the right hand side. So therefore I can write I0 is equal to Vs by 2R into 1 minus e to the power minus RT by L. This is the one thing, minus I0 into e to the power minus RT by L. So you can check the I0 is this expression we are having, right? I0 is this expression. At t is equal to 0, it will be I0 is minus I0, right? As t go on increasing, we'll be getting the, yes, waveform, whatever we have drawn, right? This type of, means it is having a combination of exponential term, okay? Exponential. Further, again, we can simplify and we can find the capital value of I0 also, but not required, okay? Next, now, if you check R load, L load, RL load, okay, whether the V0 waveform is same or different. If you check R load, RL load, RL load, V0 waveform is same na in all the three cases, okay? So please keep it in mind. In a voltage source inverter, the output voltage waveform is independent of your load, but the load current depends on, okay, your load. It depends on your load, because you check for resistive load, we had a I0 waveform is a square wave. For inductive load, purely inductive load, we had a I0 waveform is like a straight line, that is a linear type thing. And for RL load, we are having the I0 waveform, it is exponential rise and exponential fall na, right? So please keep it in mind. In a voltage source inverter, same point you will understand in a single phase full bridge inverter also, okay? In a voltage source inverter, as the input voltage is constant, so output voltage waveform is a independent of your type of the load or the nature of the load. But I0 waveform, it depends on, it varies according to the nature of the load, right? So now, so this is the yes. Now can we write the expression for V0 Fourier series expression? Yes, we can write. Let me write Fourier series expression. I0 is same na? Sorry, V0 waveform is same. So that's why I can write V0. The waveform, whatever the Fourier series expression we wrote in the previous case, the same will be here. Yes. Yes, repeated here. So summation over n is equal to 1357 up to the infinity. It is a 2Vs divided by n pi into sine of n omega t. This is your V0. What about the I0 now here? I0 is in general whatever we wrote now. 1357 up to the infinity. It is V0 by impedance. So it is 2Vs divided by n pi into Zn into sine of n omega t minus phi n minus phi n. Load is RL load now. Load is a RL load. So Zn means what here? Zn is equal to under root R square plus n omega L bracket square na. And phi n is tan inverse of n omega L divided by R. Tan inverse of n omega L by R. Is this clear? Right? So now from the V0 waveform, we can write the V0 RMS directly. But in order to find the I0 RMS, I need to find the I01 RMS, I need to find the I03 RMS, I05 RMS, and next I can find the I0 RMS, right? How to find, I will, yes, we'll discuss. Is this clear? Right? This is for RL load. Now, let me write V0 RMS. From the V0 waveform, you can write V0 RMS directly. It is a Vs by 2 na. It is like 1 by t integration from 0 to t by 2, Vs by 2 square d dt. Okay. And next plus minus Vs by integration from t by 2 to t minus Vs by 2 and those things. Okay. So same V0 RMS as that of your purely resistive load. V0 RMS is Vs by 2. Again, this V0 RMS is equal to under root your V01 RMS square plus V03 RMS square. Same thing we discussed in the rectifier chapter also. V05 RMS square and so on. Right? What is V01 RMS? What is V01 RMS? RMS value of fundamental frequency output voltage. V03 RMS value of third harmonic frequency output voltage. V05 RMS value of fifth harmonic frequency output voltage. Yes or no? Right? So now how to find the I0 RMS? I0 RMS is equal to under root I01 RMS square plus I03 RMS square plus I05 RMS square and so on. Is this clear? Right? So directly from the waveform of I0, I cannot find the I0 RMS. But with this thing, okay, by considering the I01 RMS, I03 RMS, because we are having the Fourier series expression, and we can easily find the I01 RMS, right? It is I01 peak by root 2, right? Like this. So this is V0 RMS into I0 RMS. Is this clear? Again, what is the power P0? Let me write. Output power at fundamental frequency. Output power at fundamental frequency. At fundamental frequency. That is P01. P01. Yes, it is equal to V01 RMS into I01 RMS into cosine of angle between these two, that is cos phi 1. We have represented angle with phi n. So n is for nth harmonic. So for fundamental it is a phi 1. Yes or no? Phi 1 means, what is phi 1? Let me write here. Phi 1 is equal to tan inverse of omega L by R, because n is 1 na? So that's why it is, instead of n omega L, now we will be having omega L, right? So similarly you can write output power at third harmonic frequency. Output power at third harmonic frequency. So it is P03, which is equal to V03 RMS into I03 RMS into cos of phi 3, where phi 3 is tan inverse of 3 omega L divided by R. Similarly, you can find in general output power. Yes, output power at nth harmonic frequency. At nth harmonic frequency, it is P0N, B0N RMS into I0N RMS into cos of phi n. And what is phi n? Tan inverse of n omega L by R. If you add all these powers, fundamental, third harmonic, fifth harmonic, seventh, ninth, 13th, 11th, etc., then we'll be getting the P0, overall output power. Are you getting the point? That is the P0. Is this clear? Right? So, is this clear? So this is for RL load. This is for RL load. Now let us discuss, or let me conclude this single phase half bridge inverter, right? So in single phase half bridge inverter, output voltage is a square wave. Square wave. It is independent of nature of load. Nature of load. It is independent of nature of load, right? This is the output voltage. Next, output current. Output current, yes, depends on nature of load. Depends on nature of load. So how it depends? Yes, let me write here. For R load, I0 is square wave, na? Square wave. They have asked the question, sir. Please be careful. For L load, I0 is, yes, it is a ramp type wave, right? Ramp. Or let me write a linear. Okay, linear. And for RL load, it is exponentially increase, exponential decrease. Okay, so exponential rise, and exponential fall. Exponential, right? Yes, is clear. Next, now general half bridge inverter are having some drawbacks. Okay, so which are those drawbacks? So, drawbacks, or you can say limitations. Half bridge inverter. Yes. What is the source utilization here? Source utilization in half bridge inverter. How to find the source utilization? You can check total available voltage is Vs. We are having na? We are having a 3-wire DC supply. Total available voltage is Vs. But in the output, how much we are getting? We are getting maximum Vs by 2 na? So out of the Vs, we are getting only Vs by 2. So the source utilization is 50% only. It is a 50%. Okay, source utilization is 50%. And this is the first drawback of the half bridge inverter. Okay, next, you can check it requires a 3-wire DC supply. It requires 3-wire DC supply. 3-wire DC supply. And third, for R load, there is no functioning of diode. Yes or no? Functioning of diodes. So these are the drawbacks of the half bridge inverter. Now let us discuss a single phase full bridge inverter. Single phase full bridge inverter. Yes, single phase full bridge inverter. Yes. It is a not ramp. We can say it is a ramp increase and decrease. You can indicate it with a triangular. It is triangular. Sorry, it is a triangular. Thank you. It is a increasing and decreasing, na? So altogether you will be getting it as a triangular. You will be getting a triangular, right? Next, let me put the heading: single phase full bridge inverter. Full bridge inverter. Yes. So now in order to overcome those drawbacks, okay, we are having the full bridge inverter. So let us discuss the single phase full bridge inverter with R load first. R load. Suppose the load is purely resistive. This is Vs, S1, S2, S3, and here it is suppose S4. D1, D4, D3, D2. Load is a resistive. Voltage is V0. Load current is a I0, right? I said this current is IS1, IS3, IS2, and IS4. Similarly, ID1, ID3, ID2, and ID4. Right? So, yeah, the waveforms. V0, T by 2, T, and 3T by 2. Okay. We'll be getting this magnitude as a Vs here. I0, Vs by 2R minus Vs by 2R. This is Vs by 2R minus Vs by 2R, right? So same T by 2, T, 3T by 2. Okay, so yes, here let me indicate S1, S2 conducts. Here it is S3, S4 conducts. And again S1, S2, right? Okay, so let us discuss the circuit operation. So for T is equal to 0 to T by 2, we are going to apply the gate pulse to switches S1, S2. Okay, so when S1, S2 are turned on, so it is S1 is on state, S2 is in on state. Current will be flowing like Vs, S1, load S2, and again back to the Vs. Yes or no? Load is purely resistive. So you can check when S1, S2 are in on state. Can I say that IS1 and IS2 and I0 all will be same? Yes or no, right? So let me write for t is equal to 0 to t by 2. S1, S2 conducts. So here IS1 is equal to IS2 is equal to I0, which is equal to Vs by 2R, right? What is the V0? You can check. Apply KVL. It is like a plus Vs minus V0 is equal to 0. Plus Vs minus V0 is 0. So what is V0? V0 is equal to Vs. V0 is equal to Vs. Okay. So V0 is equal to Vs. I0 is equal to Vs V0 by R. That is a Vs by R. Right? I0 is a Vs by R. That is a V0 by R. Okay. Next. So this is for t is equal to 0 to t by 2. You can check Vs output voltage, and here it is Vs by not 2R. This should be the R. Please correct. This should be the R only, right? So S1, S2 are in on state. At t is equal to t by 2, we are going to turn off the switches S1, S2. Okay. And we are going to turn on the switches S3, S4. Switches S3, S4 are turned on. So S4 and S3 are turned on. S1, S2 off. So when S3, S4 conducts, current will flow like Vs, S4, load, S3, and again back to the Vs. In this loop, the current is flowing. Yes or no? So if the current is flowing into this loop, current is like a clockwise. So what is the I0? I0 is positive or negative? I0 is negative. Yes or no? I0 is negative, because you can check current in this branch. It is flowing from right to left. I0 is negative. What about the IS3, IS4? IS3, IS4 are positive. IS3, IS4 positive. I0 negative here. Okay. What about the V0? Can we apply KVL? Plus Vs plus V0 is equal to 0. Plus Vs plus V0 is 0 means V0 is a minus Vs. V0 is a minus Vs. Okay. So let me write here. For t is equal to t by 2 to capital T. For t is equal to t by 2 to capital T. Yes. S3 and S4 are in a on state. So it is IS3. So let me write first V0 is equal to minus Vs. I0 is equal to V0 by R, which is equal to minus Vs by R. So I0 is a minus Vs by R, V0 is minus Vs. What about the IS3, IS4? You can check IS4, IS3 are opposite to that of the I0 now. So can I write IS3 is equal to IS4 is equal to minus I0, which is equal to Vs by R only, which is equal to Vs by R. Is this clear? Right? So switch current is positive. Switch currents are positive. Load current is negative. Okay. So we're having this type of waveform for V0, and here it is I0. V0 is minus Vs. I0 is minus Vs by R. S3, S4 conducts. And after T, again the same repeats. Again the same repeats. Okay. So now you can check here the V0 waveform is a square wave only. Yes or no? Right? Same as that of the previous case. But the thing is, in the half bridge inverter, the V0 waveform had a magnitude of Vs by 2, but here it is a Vs magnitude. So magnitude is doubled here. Okay. So source utilization here is 100%, we can say, because source available voltage is Vs, and in the output also we are getting the Vs. So source utilization is 100%. Is this clear? Definitely in the resistive load, there is a no functioning of a diode. Same problem was there in the half bridge inverter. Here also in the full bridge inverter also, in the resistive load, there is a no functioning of a diode. Right? Next, now can we write V0 RMS expression? Yes, V0 RMS. V0 RMS. Either you can simplify by using the expression, or you can directly by observing the waveform also we can tell. V0 RMS means square root of mean of squared value. Square of this positive is positive only. Square of this negative is again positive. So V0 square waveform will be like a Vs square waveform, na? Right? So under root of the average will be Vs square, under root will be Vs only. Okay. So, right? Yes, it is a Vs only. So V0 RMS is equal to Vs. Either you can write by using the expression, okay, or simply by observing the waveform also we can take. What is I0 RMS? You can write it is V0 RMS by R, which is equal to Vs by R. What is load power P0? It is a V0 RMS into I0 RMS. right? So this is the load power. Load is purely resistive. Okay. Now can we write the Fourier series expression? Yes, Fourier series expression. Let us first write for V0. Yes, same nature as that of the half bridge inverter. The only thing is magnitude is doubled. Okay, so V0, I am writing it as n is equal to 1357 up to the infinity. In the half bridge inverter, it was a 2 Vs by n pi. Now it is a doubled, na? So it will be 4 Vs by n pi into sine of n omega t. Are you getting the point? Simply I multiplied this magnitude with a 2. Okay, 2v instead of 2 Vs by n pi, now it is a 4 Vs by n pi, right? Similarly, what is I0? I0 is equal to summation over n is equal to 1357 up to the infinity. It is a 4 Vs divided by n pi r, right? It is a resistor is there. Okay, so into sine of n omega t. Again, you can check. V0 consists of fundamental, third, fifth harmonics. I0 also consists of these harmonics, right? I can write output voltage at fundamental frequency. Output voltage at fundamental frequency. Output voltage at a fundamental frequency. So it is V01 is equal to 4 Vs divided by pi into sine of omega t, na? Sine of omega t, right? So V01 peak, it is 4 Vs by pi. It is a 4 Vs divided by pi. So what is V01 RMS? It is 4 Vs by pi divided by root 2, na? So it is like a 2 root 2 into Vs divided by pi. You can check 2 root 2 by pi. You will be getting it is a 0.9 into Vs. Okay. So you can check V0 RMS is Vs. V0 RMS is Vs. And V01 RMS is 0.9 Vs. Means can we say that in the output voltage 90% share is of fundamental and remaining 10% we are having the harmonics. Okay. So similarly I can write V03 RMS is equal to 1 by 3 into V01 RMS. Right. And in general V0n RMS is equal to 1 by n into V01 RMS, right? So similarly, we can find I01 also, right? So output current at fundamental frequency. Let me write it as I01 is equal to 4 Vs by pi r into sine of omega t. So I01 RMS I am writing, it is 2 root 2 Vs divided by pi r. This is your I01 RMS. Okay. Similarly, you can write I03 RMS and those things. Okay. So what is the output power at fundamental frequency? Output power at a fundamental frequency. At a fundamental frequency. It is P01 is equal to V01 RMS into I01 RMS, okay, into cosine of the angle between V0 and I01. But what is the angle between V0 and I01? It is 0 degree, na? So cos 0 is 1. So that's the only thing is this one. Okay. Similarly, you can write in general, P0n, that is the output power at nth harmonic frequency. V0n RMS into I0n RMS. Okay. So similarly, you can find the total power is P01 plus P02 plus P03 up to the P0n, right? And that will be matching with your P0, whatever we wrote, na, V0 RMS into I0 RMS, right? Both will be matching. Okay. Okay. So this is about for purely resistive load, right? So stop here. In the next class, tomorrow session we'll discuss about the L load, RL load. After that, RLC load. Okay, and next we'll be discussing about some numericals, and after that the three-phase inverters. Okay, right. Day after tomorrow we'll be having a session from 2 to 8:30. Okay, afternoon 2 to 8:30. Right, we'll be finishing by 10th. Right. Yes. Ramakrishna, when there are no use of the diodes, then why they actually the circuit is it is a generalized circuit, na, right? Suppose once the circuit is designed, whether that manufacturer or the designer will be knowing that for which load we are going to use that circuit, no, na. So by default we need to keep the diodes there, but if you are connecting the load as a resistive load, then definitely those diodes will not be functioning. Right. ESC extra syllabus you will be getting in the deep learn pre-recorded videos. Right. Siva. Switches can be SCR. Right. Switches can be SCR, but most probably it depends on the switching frequency, right? Generally the MOSFETs are preferred. If you use the SCR, the thing is we need to use the forced commutative circuitries, na? So that will be again added circuitry there, right? So it will increase the complexity of the circuit, and the SCR is having the limitation like switching frequency of the SCR is somewhat lesser, na, compared to that of your MOSFET and other devices, right? So that's why generally the MOSFET or fully controlled switches are preferred, right? But we will discuss while discussing the RLC load. In the RLC load, if we are having if we select the values of resistor, inductor, and capacitor such that if our circuit is a underdamped circuit, then there is a possibility of load commutation. Means there we can use the SCR also, and even though after using the SCR, we need not to go for the forced commutation. Okay, in the RLC load you will understand it, right?
Hello.
Yes.
Sir, I draw the waveform of a VL from in the single phase half bridge.
What?
Sir, that is the half bridge inverter.
Okay, single phase half bridge inverter. In that
I draw the waveform of a VL.
VL waveform.
VL, yes.
You have drawn.
By L into di by dt, d output by dt.
Okay.
Then I got the expression that is Vs by 2 plus I not R into e to the power minus Vs by 2 plus I1 into R.
I1 into R.
Whole multiply into e to the power minus t R by L.
Okay.
Okay. From here, we can see that is Vs by 2 plus I1R means that is some extra term is there.
Please let me know which expression you have derived VL.
Sir, that is RL circuit.
RL circuit you are saying. Okay.
RL load. Okay.
Yes, in this.
Yes, sir. Then from that is 0 to T1, I am 0 to T by 2. Same expression will be get.
0 to T by 2. Yes.
Okay. Then we are getting Vs by 2 plus I1 into R. Means that term is VL term is that voltage is opposing Vs, means polarity.
Okay.
Sir, any possibility of that S1 is reverse bias, means we can't able to switching on because we assume that we are switching so that the waveform is like this. Is there any possibility that will be the Vs by 2 is less than that Vs by 2 plus I1 into R term, means that VL load means overall.
VS
So
by
that
2 is
S1
less
is
than?
on. So that S1 is reverse conduction mode, reverse mode, so that S1 will be not triggered.
Okay, okay. Means you are saying, is there any possibility?
In
You have
practical.
okay, okay. Means you are saying that VL minus I0 into R.
Is
Okay,
it?
that is nothing but the load voltage. No, that is no, sorry,
That
VL
is great.
minus I0 R. That is nothing but VL. You are saying.
That is
Okay.
overall. That is V output is greater than Vs by 2, so that the switching is not happening. Means at any possibility.
Okay, 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 okay. The thing is here, this is happening. You can check during 0 to T1 and during T2 to during T by 2 to T2.
2 to T2. Okay.
Yes. What is happening here? Even though we applied the controlling signals to the respective switches, but our switches are not turning on. The meaning is whatever the voltage here, because you can check during during T by 2 to T2, what is happening? Initially, it is like inductor has stored the energy, na? So inductor stores energy means polarity will be plus here, minus here. Right? When S1 is in a conduction mode, I am saying. Right? So after that, what will happen? We are turning off the S2 and we are turning applying the controlling signal to the S2. So our inductor will go on releasing energy like plus here, minus here. So it is like inductor voltage is greater than your Vs by 2 and the drop in the resistor.
Yes.
That's why our switch S2 is not in the conduction mode.
Yes.
Right?
Yes, sir.
Means even though we have applied the controlling signals, but then also it is not turning on because the inductor voltage is greater.
Means I want to know that by varying L and R value, is there any possibility that we are not getting that negative current value? Because is sir minus I naught and plus I naught having magnitude same?
Yes, yes. Your T1 and T2, these intervals are na. These intervals depends on your L and R value.
L and R value.
And at
Yes.
the same time, your Vs by 2 value also, supply voltage value also. Right?
Means,
if you reducing the L value, then it is like your T1 will be moving towards the 0.
Yes.
Means lesser or reverse bias will be getting for those respective switches. Right?
Yes, yes. Sir, same circuit, another doubt is.
Yes, yes.
The current is for T1, that is negative.
Current is
negative
during 0 to T1.
T1. This is negative.
Yes.
Then the inductor, when I draw the waveform, I getting that inductor VL value is positive till T by 2.
Positive till
0 to T by 2.
You are saying VL is positive till 0 to T by 2.
Yes. From the expression. Vs by 2 plus I1 into R.
Okay, okay. Actually, the VL should be negative during T by 2 to T2.
T by
Inductor releases energy.
But that expression actually
same expression of I0 or your
yes sir, same expression that Vs by 2 R into 1 minus e to the power minus T by R minus I1 into e to the power minus.
That is there only during 0 to T by 2.
And that voltage,
you can check the slope is like this. Slope is negative here. So we need to modify that expression.
Yes, sir.
For this waveform, whatever the expression, what you have done, this waveform's expression you have used of here also.
Yes, sir.
This we cannot do, na? So that's why
here we can. And when I go for VL into dt, whole integration 0.
Yes.
For that inductor, current is changing 2 times. Means for each half cycle, means for a whole T cycle, current charges or discharges means 4 times. Means plus T by 2 times means charges discharges in a T by 2 to T, again charges discharges.
Okay.
Is it
inductor
happening?
Actually it is inductor.
Inductor means two times.
Inductor is
Chalo,
storing
over.
energy, releasing energy 2 times.
But that voltage will be for only two, only not 4 times, that is 2.
Inductor voltage will be
For positive, for 0 to t by 2, again negative for t by 2 to t.
yes. That will be 2 times.
But that current is 4 times actually, means charging discharging, again charging discharge.
You do one thing, find the waveform, find the expression of this I0 during t by 2 to capital T, right?
Yes,
And after that you can check, right?
that you have already derived, sir, already.
No, I have derived 0 to t by 2.
Okay.
T by 2 to t also we need to derive, no? Right? Okay, yes.
Okay, sir. After I completing tomorrow.
Yes, contact me. Okay. Yes.
Good evening, sir.
Good evening.
Sir, what is the actual meaning of the form factor, sir?
Form factor, actually it is the just a minute, yeah, ratio between your RMS and average.
Yes, sir. I know from formula,
Huh.
but if anyone asks that question, what we can do in the theoretical form?
Okay. I will let you know, right? What is that
Okay, sir.
physical significance and where we are using it, right?
Okay, sir. Sir, one more, sir.
Huh.
We are discussing all these only R, RL, and RLE. Why you not considering the capacitor, sir, in that?
In this,
Not only in that, from rectifier and chopper, we are only focusing on the R, RL, RLE.
is you can check which type of load we need to discuss. It depends on which circuit is that one. You can check for the rectifier, the output is DC. And generally in real life, which kind of loads we are connecting to the rectifier? We are connecting the heater load, yes or no? That is
Yes,
just
sir.
like you are connecting the DC motor load, just like your RLE load, right?
Yes, sir.
Whether we are using the capacitive load on a DC in real life, no.
But in rare cases, you can use no, sir, capacitor loads also.
In rare case, we have considered also for that
Well-
half your uncontrolled rectifier with the capacitive load.
Okay, sir. Okay, sir.
Right? That is only for understanding, right?
Okay, sir. Okay, sir.
And if you check in this circuit, it is inverter circuit now we are having. Here the RLC will be discussing in the full bridge inverter. Okay, at that time you will understand for the RLC what is happening. Okay.
Okay, sir. Thank you, sir.
Okay. Yes.
Hello, sir.
Yes, please.
Sir, 278 slide number. Slide number 278, sir.
278.
Yes, sir.
Yes.
Yes, sir. Sir, here we have taken in the first expression VDC by S is equal to L S I of S minus I0. Sir, here why we are taking minus I0 actually?
It is the initial voltage, na inductor. Sorry, inductor initial current.
Sir, but why we are separated it, not added this?
No. Actually, the thing is, if you check the in Laplace transform, we are having the two properties. One is without initial condition, and the second one is with initial condition.
Yes, sir.
Here we need to use with initial condition property.
Okay, sir.
Here I cannot use the without initial condition property. Then I will not get the correct answer, na, because they have given inductor is initially carrying a current of 200 ampere, na, and capacitor also initially charged to the 100 volt.
Yes.
So that's why we need to consider this initial condition, and this is also the initial condition, right?
Okay, sir. Sir, means in case of capacitor, we have take a plus sign.
Yes. In the case of capacitor, is a plus sign, because the thing is after T the capacitor is again charging, na?
Yes, sir.
And you can check after T inductor is like releasing the energy.
Yes, sir.
So that's why here it is plus here and it is a minus here.
Okay, sir.
Hello, sir.
Yes, please.
Sir, effective time period means where TA on and T1 both will on, no sir?
Effective time period means
Both thyristor means main thyristor and auxiliary thyristor both will be on, no, in that time period.
Time period, the meaning is till which time interval your output voltage is non-zero. You can check in
Okay.
that example, na? You are saying about the numerical only, right?
Yes sir.
So you can check in that numerical during T is equal to 0 to T2. It is like a main thyristor is in on state.
Yes sir. VS.
From T2 to T3 also we are having the output voltage is non-zero, na?
Yes sir. 2 VS. Yes sir. Good.
And then from T3 till capital T, output voltage will be 0. So effective on period means we need to consider 0 to T3.
Okay sir.
Right? The interval during which the output voltage is non-zero. Right?
Okay sir.
Yes, next.
Sir, good evening, sir.
Yes, good evening.
Sir, in 331, sir.
331. Okay.
321, sir. 321, sorry. Sir. 321.
Okay. Yes.
Sir, in this, could you please explain I0 waveform, sir?
I0 waveform.
Yes, sir, I0 waveform.
Okay. The thing is here you can check. Let us start.
Sir, hello, sir.
Hello. Hello. Am I audible?
Yes sir.
Sorry, sir.
Okay. In between, I think there was an issue. Yes. Yes. Hello.
Hello, yes, sir.
You only asked the question, na?
Yes, sir.
For
That
the
I0.
I0 waveform.
Yes, sir.
So did you get whatever I explained, or I don't know, miss, whether I was there or it is disconnected? I don't know.
Sir, it is disconnected, sir, from the beginning also, sir.
Okay. Just a minute. I will explain again. Okay. So what is happening here? From T/4 to T2, S1 is in a conduction mode.
Sir, S1 is conduction
Yes.
mode.
So S1 is in on state. Current is flowing like this, clockwise direction.
Yes, sir.
Inductor
Yes, sir.
stores energy.
Stores energy. Yes,
So
sir.
that's why current is positive.
Yes, sir. Okay, sir.
At T/2, S1 is turned off. We are turning it off. It is not turning off by natural commutation. Please be careful. We are turning it off.
Okay, sir. Okay.
Right? Means indirectly, if suppose this is a MOSFET na S1, then I am removing the VGS signal. That is the gate to source voltage. Right?
Yes, sir. Okay.
So
sir.
next what will happen? This inductor you can check corresponding to T by 2 current flowing through the inductor is a positive, it is a non-zero current.
Yes, sir.
So next what will happen? This inductor will release the energy through diode D2.
Yes, sir.
Means
Okay. sir.
even though we apply the controlling signal through the switch S2, our S2 will not turn on immediately because this inductor will oppose the, right? Inductor will oppose the conduction of this switch S2. So diode inductor will release the energy. So here inductor releases energy. In that case also you can check current in this branch is from right to left only. So that is nothing
Sir.
but current is positive only. So positive and it is decreasing.
De-
Next at
decreasing.
3 T by 4 S2 is in a conduction mode. So when S2 conducts, current will be flowing in this loop, lower loop. So
Sir.
current is in the clockwise direction. So I0 will be positive or negative. It is a negative,
Zero
na?
will be negative, sir.
Right? So inductor again stores energy. So here current inductor is storing the energy. So current is increasing. This will continue till capital T. At
Yes, sir.
capital T, S2 turns off, and inductor
Okay,
releases energy through D1. Right? So like this. Okay. So
Okay,
you
sir.
need to understand how the inductor stores energy, how the inductor releases energy, right?
Okay, sir. Sir, in 325, sir.
325.
Yes.
Yes.
Sir, I did not get the waveform, sir. IS2 and ID1 and ID2.
Okay. Okay. The first thing is, yes, for this circuit we draw. No? Yeah. Try to understand here. When S1 is in a conduction mode, let me write here. When S1 is in a conduction mode means current is flowing like this, na, clockwise direction.
Yes, sir. Clockwise
IS1
direction.
and I0 both will be same or different.
So both will be same.
Yes, IS1 is equal to I0, right?
Yes, sir. Yes, sir.
Second thing, when S2 is in a conduction mode, current is flowing like this, na, clockwise direction.
Sir, clockwise
So
direction.
whether IS2 and I0 both will be same or different,
Sir, both will be
Opposite.
different, opposite.
right? One is, this is in downward direction, this is in like this. Na. So it is
Yes,
like, can I write IS2 is equal to minus I0,
Minus, yes, sir.
right? Next, when D1 conducts, sorry, diodes, yes, for this diode also there. When D1 conducts, current is flowing like this, na.
Yes, sir. Current is
So
flowing
you
upward.
can check when current is flowing in this direction, what is the ID1 and I0? Both will be same or opposite?
Opposite, sir.
Opposite. So can I write ID1 is equal to minus I0?
Minus I0. Yes,
And
sir.
when D2 conducts, current is like this.
Yes, sir. Same
Check
direction.
ID2 and I0,
Same direction, sir.
same direction. Now with this only, we need to draw the waveforms. You can check first for IS1. IS1 is same as of the I0 now.
Yes, sir. Same.
Right? So here you can check S1 is in a conduction mode from T by 4 to T by 2.
Yes, sir.
So from T by 4 to T by 2, I0 waveform is like this.
Yes, sir.
So only this part of the I0 waveform we will be getting it as IS1 na?
Yes, sir. Yes, one.
This it is positive, so that's why it is also positive as it is, right?
Okay. Yes, sir. Okay.
Similarly, after this again here it is S1 conduction mode, so that's why the same waveform I have repeated here. Okay.
Okay, sir.
Next, let us check for IS2. We know IS2 is minus I0 na?
Yes, sir. Minus I0.
I0. Now where S2 conducts in this means first, second, third. After 3 means fourth interval S2 conducts.
Yes, sir. Fourth interval.
Right. So S2 conducts in the fourth interval, and IS2 is opposite to that of the I0 na?
Yes, sir.
So I0 is negative here. During this interval, when S2 conducts, I0 is negative. So how will be the IS2? IS2 will be opposite to that of this one, means like this only.
Sir, inverted. Okay.
Right? Positive direction. Positive value.
Two direction.
Opposite to that of this one means IS2 should be positive. You can check IS2 waveform, you will understand. IS2 here, 3T by 4 to T by 3T by 4 to T, IS2 is like this.
Yes,
During
sir.
this interval, actually I0 is negative, but IS2 is positive.
Positive.
Right? Similarly, you can check here ID also, ID1 na. Let me write ID1. ID1 is minus I0 na. Where
Okay,
diode
minus-
D1 conducts here, and here it is also.
Yes, sir.
So I0 is negative here. So I0 is
Negative.
decreasing and negative. So how will the ID1? ID1 will be exactly opposite to that of this one. Na? If here I0 is minus I0, then ID1 will be plus I0.
Yes, sir. Plus
After
I0.
that I0 is it is decreasing, negative decreasing, ID1 will be positive decreasing. right?
Positive degrees.
You can
Okay,
take
sir.
ID1 waveform, you'll understand. Yes, I think, yes, ID1 it is from I0 to it is positive decreasing, right?
Positive degrees.
Similarly, you can
Yes,
check
sir.
for ID2 also, right? You can check for ID2.
Okay,
ID2 is I0, you will be getting them, right?
Okay, sir.
Okay, okay, yes, yes. Yes, next.
Hello, sir.
Yes, Akshay.
Sir, like, is there some specific reason why we are calling the type D chopper two quadrant type B chopper specifically?
Actually, the thing is, you can check the operation. Those particular choppers allows voltage and current in a particular direction only, na?
Operation.
So based on that, they are having the types, right?
Oh,
And those types are based on the
Hmm.
quadrant of operation only.
sir,
Type
but like
ABCD, type ABCD, they have given simply the names ABCDE,
okay, okay.
right? It is
Yes,
not like
yes,
that
sir.
there is a behind any theory is there. No, type ABCD, these are simply the names. Okay.
Okay,
So these
sir.
are the basic. A and B are basic actually, and after that we are having the C. C is like a combination of A and B, right?
Okay, okay, sir.
Right.
Sir, like one more thing, like, are we going to cover, like, discuss the basics of drives in coming class or
Basics of
drives,
which
drives, electric
Triac.
drive? Yeah.
Switch triac.
No, sir, drives,
No,
DRIVES.
drives we are not going to discuss, because as long as the gate examination is considered for gate syllabus, the drive is not there, na? Drive you will be getting in that deep learn platform. You are a ESC student or gate student?
Gate students.
ESC student?
Gate students, sir.
Yeah, so for gate the drive is not there,
Okay, sir.
right? For
Okay.
ESC they are having the drive fundamentals of electrical drives. Okay, they will be
Okay.
getting that in a deep learn platform. Okay.
Okay, sir. Okay, sir.
Okay.
Got it. Thank you, sir.
Yes.
Hello, good
Yes,
evening,
Salman
sir.
Khan.
Hello, sir. Good evening.
Yes, please. Good
Sir,
evening.
how energy releases from inductor, sir? There is no resistor and else means at one point the inductance voltage and source voltage will become same and there is no current flowing, no, sir?
Please repeat and please speak a bit louder.
How inductor releases energy, sir, in purely inductor circuit? Means I am thinking that at one point the inductance voltage, that is voltage energy across the inductance and the source energy will become same and there is no energy flow between them. Means inductance energy will never become below the source energy.
Inductor voltage will never become the source below that of the source energy.
Yeah.
How you can say like this?
The inductor stores energy when S1 is closed in this circuit, sir.
Okay.
Then after S1 is opened and it starts releasing from opposite direction, means in the Vs by 2 and D2, this circuit.
Okay.
At one point that energy will become equal to the Vs by 2. Then
Okay.
after that how it becomes less than that, means there is no potential difference. I'm thinking that.
No, potential difference is not happening, but the thing is, in the circuit we're having a source, na?
Yes, sir.
Our source is absorbing that energy.
Source is absorbing the energy.
Yes, you can check here. T/4 to T/2, you can take the product of V0 I0.
Yes, sir.
It is like a power is positive.
Right, sir.
So it is like when inductor stores energy, it is like power is flowing from source to the load.
Right.
Here you can check voltage is negative, current is positive, power is negative.
Right, sir.
Power negative is the meaning is power is flowing from load to the source. So our source is absorbing that power.
Okay.
You can check simple circuit. Suppose in the circuit I am having, let us consider two voltage sources. Okay.
Okay, sir.
Whether out of that one is having the lesser voltage and second one is having the higher voltage. Okay. And
Okay.
suppose a very small resistor is also there, right? So what will happen in that case? whether the voltage source will consume the power?
No, sir.
No,
Resistance will dissipate the power, na, sir?
no, but voltage source also will consume the power. Let me, you can please draw the circuit.
Yeah, I understood, sir. Understood.
Yeah, suppose at one side we're having a 10 volt voltage source, at second side we're having suppose the 5 volt voltage source. Okay,
Right, sir, right. It will
both are having the positive plates at the upper side, negative plates at the lower side, and in between consider very small resistor. You will understand, right?
Yes, sir. Yes, sir. Power balance equation, sir.
Yes, yes, yes. Okay,
Sir, understood. Thank you.
right, right. Yes, next. Yes, please.
Sir, in RL load,
In
is
RL
half
load,
bridge, sir.
half bridge inverter.
Yes, sir.
Yes.
Sir, in this I0 waveform, is the time interval T1 to T/2 equal to T/2 to T2? That two time intervals, are they equal?
Okay, okay. No, T1 to T/2 and T2 T/2 to T2, these are not equal. 0 to T1 and T/2 to T1 T2, those two will be equal.
Yes, sir.
Just a minute. Let me tell you. Here inductor is storing the energy and here it is releases energy. Yes. Correct. You can check this T1 and this T2 varies according to your R and L, na?
Sir.
Right? So here what is happening, 0 to T1, it is like a inductor releasing the energy. Means it is coming from minus I0 to the plus 0. Okay.
Yes, sir.
And from T1 to T/2, inductor is storing the energy.
Yes,
So
sir.
for this much interval, it is storing the energy. So from T/2 to T2. Okay. But when inductor is storing the energy, you can check when S1 is in a conduction mode, it is like inductor is storing the energy. Here it is a Vs/2 and here it is RL.
Yes, sir.
When S1 is turned off, our inductor will go on releasing the energy, na?
Sir.
To diode D2. Right?
Sir.
So probably yes, you can say T1 to T/2 and T/2 to T2 both will be same, right?
Sir,
Because the circuit, we are having the same circuit, na?
sir.
Right.
Similarly, T1 to T/2 will be equal to T2 to T also, na, sir?
Please repeat. T1 to
T1 to T/2 will be equal to T2 to T.
T2 to T2 or small T2 to T.
Small T2 to capital T.
No. T1 to T/2 and this T2 to T, these are not equal.
Okay.
These are equal. You can say T1 to T/2, T/2 to T2, these are equal.
Sir.
Right? In other way, you can say 0 to T1
Sir.
and T2 to T, these can be equal.
Okay.
Right?
Okay, sir.
Because it is like for storing the energy, it is having this much of time. So for releasing the energy here, right, it will be taking this type of time, this much of time, right? Once you get the I0 expression, na, whatever we have written,
Sir.
in that you can check, can I put at T is equal to small T1, I0 is 0?
Sir, I not get, sir. What, sir?
Please, I0 expression I have written.
Sir.
In that expression, do one thing, put T is equal to T1
Okay, sir.
and replace I0 with a 0.
Okay, sir.
From that, you will be getting T1 value.
Sir.
Right? So similarly, we need to write the expression for this waveform also.
Sir.
This waveform expression will be same as that of this waveform expression. The only thing is sign will be negative and the time we need to consider T is equal to small t minus T/2 because this is effective only from T/2, na, this waveform.
Sir.
In that waveform also put T is equal to T2. In that expression also put T is equal to T2 and put I0 is equal to 0. You will be getting T1 and T2 and then you will understand whether this T1 and T2, what relation they will be having.
Oh.
Right?
Okay, sir.
Okay.
Sir, and
but these are not passing through center. This T1 is not like a center of this T0 to T/2. No.
Okay, sir. हाँ, sir.
Right? It depends on the RL value.
हाँ.
Right.
Okay, sir. हाँ.
Huh.
Sir, and could you tell what is source utilization? I not get it, sir.
Okay. Source utilization means you can check here. We are having total available source voltage is Vs na.
हाँ, sir.
This is Vs by 2 plus Vs by 2 means Vs.
हाँ, sir.
Out of that, across load, how much you are getting maximum? It is a Vs by 2.
हाँ, sir.
Or RMS value of V0 is Vs by 2 only, na, we are getting.
Yes, sir.
So the meaning is we are having the available voltage is Vs, and in the output we are getting only Vs by 2. So source utilization is only 50%.
Okay, sir.
Right? But in the full wave, you can check whatever the for purely resistive load we discuss na, full bridge inverter. Output
sir.
voltage is Vs, available voltage is also Vs. So source utilization is 100%.
Okay. हाँ, sir.
Right? Okay.
Sir, हाँ, sir. Sir, and those disadvantages which you told for this inverter, could you just
Average.
briefly tell them once again? I not get it that.
Okay.
Thanks.
Yes. Source utilization 50%. It requires a 3-wire DC supply. 3-wire DC supply is generally not used, right? 3-wire DC supply is a specially designed DC supply actually. But for half bridge inverter, we require it, na? Right?
Yes.
So that's why it is a limitation or the drawback of the half bridge inverter.
So where do we use this 3-wire DC in the input side?
We are using it na for half bridge inverter. Yes, here you can check. This is a 3-wire DC, na 1, 2, 3.
हाँ, sir.
This is a DC supply, but whether it is having only 2
Huh.
wires, no, it is having a 3 wires. Right? So that's why this is the one disadvantage. Next one is for purely resistive load, that there is no functioning of a diode.
Sir.
Right? So that is also the drawback. Means on our board, actually the diodes are there. In the circuit, the diodes are there. Okay. But the
Yes.
thing is, the current is not flowing or the diodes are not in operation na, for purely resistive load. So
Sir.
this is the drawback actually of the design, actually drawback of the design, right?
Okay. Okay, sir. Thank you, sir.
Yes. Okay.
Sir, hello, sir.
Yes, please.
The same disadvantage will be there in a full bridge also, na, sir? R load, there is no functioning of diodes.
Please repeat.
There will also be the same disadvantage in the full wave.
Yes. For full bridge inverter also, for R load, there is no functioning of a diode.
Right, sir.
So for full bridge also, that will be the disadvantage, right?
Right, sir. Okay, sir.
Okay. Yes. Why diodes are used in these inverters? Manikumar, the diodes are used because in order to feedback the power na, to the load. You can check RL load, L load. Definitely for purely resistive load, there is no functioning of a diode. But for RL and L load, there is a functioning na. Prasad, the class is there from 2 p.m. onwards on day after tomorrow, okay? On Ganesh Chaturthi. Yes. Okay, right. Okay, so we'll stop here. Thank you. Thanks to all of you.
Thank you, sir. Good night.
Yes.